Good morning to everybody. It's our last day of this long week with very interesting talks. Thank you, everybody, for being here. Today we start with LHCb results by Martino Borsato. Please.
Yeah. Thanks very much for having me. It was nice being here at this conference. And thanks for the people who are still here today for my talk. So yeah, I'll be talking about indicted searches for physics beyond the standard model. And I don't think I need to convince you. I've heard this argument many times in this conference that quark flavor changing processes are an excellent indicted probe of physics beyond the standard model. You know, you can take, if you don't take flavor structure for new physics, you can get flavor observables to reach new physics scale in their sensitivity, which are way, way beyond the reach of our colliders. Look at the scale of this plot here. And that means basically that they are already shaping the landscape of beyond standard model theories up to very high energies. And that led, for example, to the answers of minimal flavor violation. And of course, one of the things that you can do studying quark flavor physics is trying to address the flavor puzzle, which is that Yukawas are not controlled by any standard model symmetry, but they seem to have some structure. And there's been tremendous progress over the last 30 years, I want to say. You can see, for example, here that very clearly on the CKM unitarity triangle, although that's not the only thing we study in flavor physics, how the determination of the position of the vertex has improved tremendously over the years. Now, I mean, in this plot from 2021, you can't even see it. You would need to zoom in. And so I want to present the LHCb experiment briefly, because this was the only talk from LHCb in this conference. And yeah, so flavor physics so several very interesting observables of flavor physics can be studied with B mesons, or B hadrons, I should say. And at the LHC, the cross-section for production of BB bar at 13 TeV is huge. We're talking half a millibar. And if you take the luminosity the LHC is able to provide, 10 to the 34, you get a rate of 5 megahertz. So this is really, as Ben said, I think yesterday, a shitload of bits. And well, the problem is that they come with a lot more stuff, right? So the inelastic cross-section is 200 times larger. So you need to reduce that. One thing is the BB bar are both produced at a very small angle, so close to the beamline, normally on the same side. And but in that region, you also have very high detector occupancy of low PT tracks, and you also have a very large boost in the forward region, which is good. We get an average of beta gamma of 20 for B mesons, which means they fly about 1 centimeter before decay. And that is excellent, because this means if we can identify the displaced B vertex, we can separate it from the primary vertex of the proton-proton collision and rule out ignore all the tracks. There's hundreds of tracks coming out of proton collisions. Now, issue is there's pileup. So if you want to run at this luminosity, you will get a pileup of about 30, meaning that although the vertex of the B we might be able to identify it, it's very hard not to be affected by random tracks flying by and crossing in something that looks like a vertex. So what we're doing for an LHCb experiment, what we've done in run 1 and 2, is to run at lower luminosity, about a factor 30, meaning that we get on average 1 collision per proton-proton bunch crossing. And in that case, of course, it's much easier to identify the B vertex. And we also build the detector in the forward region of the proton collision. So the proton collision is happening on this side, and that's our detector. We need, of course, excellent vertex identification, because we want to separate the secondary B vertex, but also because we want to measure very precisely the B lifetime and oscillations. We need low PT triggers. Your PTs will be all the order of the mass of the B or less. So we need to go as low as few GeV, which of course is quite challenging for LHC. We have a dipole magnet and precise tracking devices to measure the momentum at 0.5% precision. And of course, we need to do particle ID. And we have special Cherenkov detectors for that, for hadron identification, which is particularly hard to do. And yeah, we can do excellent B physics with that, but I should say, LHCb by now doesn't do only B physics. It was a very successful experiment, and it has a broad physics program in the LHC forward region. A few words on results of flavor physics from LHCb. I only have one very general slide. I'm sorry for that, but of course, time is limited. And I thought I would just pick some world best measurements that the LHCb detector provided. We measured the mixing in both the BD and BS system. We measured the CKM angle gamma to world best precision to about 4 degrees. We got the CP violating phase in the BS system. This is a very small value in the standard model, and it's very sensitive to new sources of CP violation. And then, of course, we have several measurements of electroweak flavor changing neutral current in B2S. This is including B2SLL decays, where the famous, let's say, flavor anomalies were detected, and I will talk about much more about it later. But we also do charm and strange physics, and the charm program in particular is skyrocketing. It's we recently detected for the first time CP violation in charm with this measurement of delta ACP, and also for the first time a significant mass difference between D0 and D0 bar, and this is this parameter XCP. And in strange, although several of the K-short fly out of our detector, we have so many of them produced that we can place world best limits, for example, in interesting decays like the K-short to mu mu, where we placed an upper limit at 10 to the minus 10 in branching ratio. All right, so as I said, since I think this is in the spotlight right now, and I've heard many people in this conference mentioning it, I will focus on electroweak flavor change in neutral current in B2S. Now, why is that interesting? This is suppressed by loop, so it doesn't go at a tree level in the standard model, and also it's flavor suppressed, so the CKM entries are small, and it's suppressed by the GIM mechanism. And for that, because of this suppression, you get decay rates that are of the order of 10 to the minus 6 or less. You see here a typical first order diagram, the so-called penguin diagram, where the loop is involving a W, a top, and either a gamma or virtual Z. These are very interesting. When being suppressed, they can get tiny BSM contribution at the same order as the standard model amplitude, so they can be very clear in this case. And they can be sensitive to supersymmetry, even if this is minimal flavor violating. And this is also an excellent experimental probe at the LHC, I want to say, because there's no neutrinos involved in the final state. It's hard to reconstruct. It's actually impossible to reconstruct such low PT neutrinos at the LHC. And there's several complementary observables, and such as branching ratio, angular observables, or one can do standard model symmetry tests. and the several complementary decay channels, the phenomenology is very large. And I think we can class them in three main types of decays. There's the radiative, B2S gamma. There's the fully leptonic, such as B and B sub S to a pair of muons. And there's semi-leptonic, B2S LL. And these can all be interpreted in an EFT below the electroweak scale. This is sometimes called low energy effective field theory, where you take out the CKM entries. You have G Fermi, and all goes in this factor here, which is constant, and it's about 34 TeV squared. And that sets more or less the scale that you are testing. And you have these operators. So you have the dipole for the radiative B2S gamma, and then you have B2S currents coupled to lepton currents, which are either vector, axial vector, scalar, or pseudoscalar. And sorry for the naming; it's a bit confusing. I'll be talking about these 07, 09, or 10, but I try to remind you what they mean in terms of Lorentz structure. Okay, and different decays are sensitive to, I have different sensitivity to these Wilson coefficients, which is very, very good because we can use, for example, the radiative to single out C7 and the leptonic to single out C10 and get a handle on all of them. All right, let me start with B2S gamma. I forgot to mention these Wilson coefficients are left-handed in the standard model, but there could be right-handed contribution. And to measure, I should say, the left-handed contribution, the best observable is the inclusive B to XS gamma branching ratio. This comes with a 5% precise prediction nowadays, and it was measured at B factories with similar precision already, and it would be improved by the Bell 2 experiment. But at LHCb, this is very hard because it's an inclusive decay. We have so many tracks flying around that it's very hard to do that. You can also measure the imagery part with ACP in B2K short by 0 gamma, and we did measure that with B sub S to phi gamma at LHCb. Now, for the right-handed, at B factories, you have, again, these B2K short by 0 gamma, and you measure mixing-induced CPV there to get the sensitivity on the right-handed contribution. This measurement is impossible at LHCb. There's 3 neutrals in the final state. There's really showing the things we can do. I mean, already having 1 neutral in the final state is quite hard. Having 3, it's impossible. We do B sub S to phi gamma and get good sensitivity with that. We do an angular analysis of the baryon decay lambda B to lambda gamma now. And the most sensitive one is actually not, strictly speaking, radiative decay, is a B2K star EE at LHCb, and we measure transversal symmetry there. And let me say a few more about that. Basically, we go at extremely low Q square in the dielectron, so that we are picking up only the contribution from a virtual photon. So effectively, we are studying the radiative decay. But having the electron in the final state means we get a nice fully charged final state. And but we have to pay the price of alpha electromagnetic, of course. Still, we reconstructed about 500 events with LHCb with a quite clean signal peak in our data. This is the invariant mass of the 4 tracks final state, and it peaks at the B mass for your signal. And then we go ahead and do an angular analysis. So because the gamma goes to electrons, you can get a handle on the polarization of the photon. And that comes from this angle phi between the decay of plane of the hadrons and that of the electrons. And if for the standard model, so fully left-handed, you get no modulation in phi, while if you introduce a small right-handed amplitude, you will get a small modulation. And if this comes with a phase with respect to the left-handed, you will also see the phase. So we go to our data, try to measure that. We don't see any significant modulation. And we translate that in a measurement of the imagery and real parts of C7 prime normalized to left-handed C7. So this is, I remind you, right-handed, and this is left-handed. And you see standard model prediction is very close to 0, no right-handed. But our constraint from B to K star E is much, much better than any previous constraint. And actually, there was a talk last year at this conference suggesting, and I mean calculating SUSY loop contribution from MSSM with quark flavor violation that is partly already excluded, or I should say tested by this measurement. So there's good prospects for this in the future, I think. Of course, I need to talk about B sub S to mu mu. This is a golden flavor physics channel. It's extremely rare because on top of the suppression I mentioned, there's helicity suppression. So we're going down to 10 to the minus 9. And the prediction, because it's a fully leptonic final state, it comes with 4% precision, which is very remarkable for this kind of decays. It was searched since the 80s and firstly observed by LHCb and CMS in 2014. Now we have updated the measurement from LHCb with a full data set we have at hand, and we reach 16% uncertainty on B sub S to mu mu, which I think is really remarkable, thinking that only a few years back we hadn't observed this decay. You can get contribution from even minimal flavor violating MSSM, and they come with dependence on tangent beta to the 6th power and MA to the 4th power. Divided by MA to the 4th power. So you can exclude, high tangent beta, low MA. We can expect about 10% precision when Atlas and CMS will update their measurement with the full run 2, which is bound to happen very soon, I think. And so combining all measurements from the LHC, we can get this fantastic precision on this 10 to the minus 9 decay. We also measure the B0 to mu mu and do a combined measurement. And this is even rarer. And this is also, so the ratio of these two is testing the MFV paradigm. And so far, it comes with excellent agreement with the standard model, although I think you can see from this plot that B sub S to mu mu is sitting slightly above the below the standard model. All right, I move to semi-leptonic. Now, I need to talk about Q square because these semi-leptonic decays are affected by a large background coming from charm. You have B to S CC bar that. And especially if this organizes as a J psi and decays to 2 leptons, you have the same final state. And but however, these peaks at the mass of the J psi or at the mass of the psi 2s, depending on the hadronization. So we can exclude these because we measure Q square. We can just veto these resonances and measure the rare loop level B2SLL decay. And actually, it's even better. We can use these peaks for our normalization. They are excellent to normalize our measurements. So we measure branching ratios away from the CC bar resonances in several final states, depending on the spectator core, essentially, and on the hadronization of the B. And you see that the uncertainty on the predictions are very large. We're talking over 20 to 30%, because there's hadronic form factors involved, there's hadrons in the final states. But there's a coherent undershooting of the measurements with respect to the predictions, which might be interesting. We go ahead and do also angular analysis. In the case you have a vector meson in the final state, you get a rich kinematic structure to be studied which can be described again by the three angles I described before. And we get, again, results in several different final states. We get B0 to K star 0 mu mu, B plus to K star plus mu mu, and B sub S to phi mu mu. They come with different sensitivity because of the statistics, and also different sensitivity because of the peculiarity. For example, this one is not self-tagged in flavor because phi goes to K plus K minus. So the angular analysis is three-dimensional. You do it in bins of Q square. And as I said, you can use the J psi to test that the procedure is correct. And we can test this against previous experiments because this is a high statistics channel. This was measured very precisely at B factories before. And we measure, as I said, many angular observables in Q square bins, so it's a lot of measurement. And standard model predictions are challenging, but compared to the branching ratios, they come with significantly smaller uncertainties. And there's also optimized observables you can build by taking ratios of observables where the hadronic uncertainties cancel out at the first order, but you still get you get better sensitivity to possible new physics contribution. So a lot of measurements, some deviations at the level of more than 2 sigma, but it's hard to draw conclusions until you do an effective field theory interpretation of that. For example, you can interpret that as a modification to the vector coupling C9, which is the one these decays are most sensitive to. And you get that a modified vector coupling C9 fits better than the standard model in all these three channels and coherently. So that becomes quite interesting. And then I have to talk about lepton universality test. So we're doing that in this semi-leptonic B2 SLL. When we of course, this is supposed to be a lepton universal. So especially when you compare the electrons and the muons, because the masses of the final state leptons can be neglected with respect to the mass of the B, the branching ratio in the standard model, the ratio of branching ratio, between muons and electrons is expected to be 1 with just a 1% or less than 1% uncertainty coming from QED corrections. The main challenge for these measurements really is to control the differences between electron and muon reconstruction in our detector. So let me briefly talk about that. The first main difference is early on at the first level of trigger. While we can trigger on very low PT muons, we need to increase a bit the threshold on PT on the electrons because we have to use the calorimeter, and that comes with a much higher occupancy. Electron ID is also a bit harder for electrons, and it's based on the measurement of the energy at the equal and a comparison of that with the momentum from the tracker. And because hadron just leave a fraction of the energy in the equal, you can see that electrons peak at 1 in this ratio, while hadrons peak lower than 1. And then you have that at the energies of the LHC, the electrons will emit a lot of bremsstrahlung as they pass through the detector material. And if this is emitted before the magnet, this will go to a different region of the calorimeter, and we need to project the direction of the track before the magnet and look for a neutral deposit in this region. And if we find it and it's compatible with being a bremsstrahlung photon, we add the energy back to the electron track. However, this bremsstrahlung photon recovery procedure doesn't have 100% efficiency. It's more like 50. And therefore, we are often losing some energy. And that translates in a bad, somewhat, worse mass resolution for electrons than for muons. So you can really see this very clearly in these two pictures, which have a very different range in masses. And that also means that there's more backgrounds coming in from lower masses where you only partially reconstruct the final state of the B. Maybe there's an additional pion that was missed, or from combinatorial, random combinations of tracks. So of course, it's harder in electron to subtract the background and measure the signal contribution correctly, and that is really the name of the game for these measurements. That said, the results from LHCb are much more precise than previous experiments, just because we have so many B decays. So you see here, for example, RK compared to previous measurements from Babar and Bell, the B factories. And again, we measured this in several B2SLL channels. And it's interesting because, again, we get an undershooting of muons with respect to electrons in all these channels, sometimes more significant, sometimes less, but definitely interesting. And I'm not mentioning charge current B2CL new lepton universality test, but of course this can be connected. We heard a lot about this. We will hear more later from Gino, I think. Yeah, so these are the famous RD and RD star. Then we can do this effective field theory interpretation all together in these different decays I've discussed. B2S gamma is very precisely measured and doesn't enter this picture because, and so basically that fixes the dipole operator. But when you look at the vector versus the axial vector, you see that you get kind of a coherent picture. Here you get B sub S to mu mu constraining just C10, and RK and RK star are this blue band here. So here I'm just modifying the muonic coupling, and this is what comes from all the measurement in B S to mu mu, so branching ratio and angular measurements. So you can, for example, take a model with a modified left-handed coupling to muons that respects V minus A, so left-handed, and that would fit better than the standard model by more than 5 sigma. But you can also try to do a more generic lepton-dependent short distance contribution. So float all the Wilson coefficients that are relevant to B2S flavor change in neutral currents, and so account a bit for the Lucas square effect in model space, let's say. And still this gets you at more than 4 sigma. So definitely interesting, although of course we need to take care because we are trying to contradict the standard model, and that requires very hard evidence. Now, what is the connection to high energy? As I mentioned, the scale is about 30 TeV, so this could be out of reach of the LHC if the coupling is of order 1. But there are ongoing searches. We've heard a lot about that. There was a plenary talk from Costas on Monday, and many more in the parallels. And you know, 3-level candidates are either a Z prime or a leptoquark with vertices involving both quark and leptons. Yeah, there were, as I said, there were several models addressing these anomalies and at the same time as others in this conference. Now, what can we do next at LHCb? We can do more sophisticated analysis of the muon final state. We have all the 10K events in our dataset right now, and we can do angular test of lepton universality in B2K star LL. That would be very interesting because it gets more sensitivity and additional sensitivity to lepton universality. And we still have to measure this lepton universality ratio in other decay channels. And we are also exploring to do this measurement at higher Q square, where experimentally it's more complicated, but we found ways. And yeah, there's also lots of potential in baryons, I should say. We have an upgrade of the detector installed, and which will run for run 3 and run 4, which upgraded completely the readout electronics as well as several sub-detectors. And so that we can run the detector at 5 times higher luminosity. The readout electronics is upgraded so that we can read out the full detector in real time. That means 40 megahertz, the LHC bunch crossing rate, and trigger. So we feed that to GPUs and trigger directly in software. So that gives us 100% flexibility on what we can do in our trigger. And that's for flavor decays, that means we can trigger directly on the displaced vertex of the meson decay. Okay? So most measurements will directly profit from the higher statistical precision that's coming from running the detector at 5 times higher luminosity. And we expect about a factor 3 better precision with run 3 only. We also plan to upgrade even more the detector in the farther future. We're talking 2030 now. It's a bit far away, but of course these projects take a very long time, so there's a lot going on already. And the plan is to increase the luminosity by another factor 10, so a factor 50 compared to run 2. And so in upgrade 1, you already get 5 pile-up collisions. In upgrade 2, you will get about 50. So that becomes really an issue, and we have to, the only reason why we think we can do that is because we plan to upgrade detectors to have a sort of 4D detector, so measure timing very precisely, so that we have another handle, not only on the position, but also on the timing to separate the primary vertices. And really, this upgrade is driven by detector developments. We don't need the LHC to reach high luminosity. The luminosity that is providing now is already good enough for our high luminosity upgrade. I think that's interesting. And so it's all about developing a detector that can do timing, have better granularity, low material budget, radiation hardness, and real-time analytic capabilities. And the sensitivity, if you project all the way to 2040 on the relevant flavor physics observables, so some relevant flavor physics observables here, is quite mind-blowing. That more or less translates to doubling the reach in terms of new physics energy scale. Okay, so concluding, there's in the history of high energy physics, we've often seen indirect effects at lower energy, anticipating discoveries of new particles at higher energy. So we hope this pattern will continue, and we have several leading measurements in precision quark flavor physics coming from LHCb, and I provide a brief review of B2S. So there's hope that an anomaly can be the first hint of a discovery. LHCb performance in rounds 1 and 2 was amazing and vindicated the detector design and motivated upgrades 1 and 2 to run at much higher luminosity. And there are some tantalizing anomalies in B2SLL decays, and I think LHCb can clarify the situation shortly with complementary measurements and also the upcoming upgrade data, which I should say is almost coming from a brand new detector, so also with different detector systematics. Of course, inputs from Atlas, CMS, and Bell2 are extremely valuable, welcome, and eagerly anticipated. We hope they can have a say on that. And we should keep in mind that these kind of claims require extraordinary evidence. So don't jump on your head if you just see a free signal. Thank you.
Thank you very much for your nice talk. We have a few minutes for questions, please.
John.
So thanks, Martino, for discussing in detail the issues that you have with the electron efficiency. So I thought that you'd been able to cross-check that with your measurements of flavor universality in J psi and psi prime decays. But I guess there's a possibility that you could do a sort of full kinematic fit. So I wonder whether that's a potential issue when you're looking at the B goes to strange E plus E minus decays.
A full kinematic fit. So you're meaning like measuring lepton universality as a function of Q square, the decay maybe?
Well, you know you're looking at a J psi or psi prime decaying into E plus E minus or mu plus V minus.
Okay,
so that gives you an additional kinematic constraint on reconstructing the event. So does that impact the efficiency that you're able to estimate?
Oh, yeah, I should have mentioned. So the measurements we're doing, maybe I even have a backup slide. Yeah, so the control channel in the J psi is integrated into the measurement because it is extremely important to normalize our measurements. What we measure is not just the ratio between the branching ratio of the rare channel in the muon and in the electron, but we include the branching ratio in the J psi channel. And since this has been measured to be, it's also expected to be lepton universal at a fraction of percent, this ensures that differences between electron and muon reconstruction that we're not modeling perfectly in our Monte Carlo cancel out in our measurement and don't impact our final result. Because here we have a ratio between electrons and here one with muons. So really the only problem is that J psi decays will have a slightly different kinematic from the rare channel at low Q square. So what you use the Monte Carlo for is to extrapolate from the Q square of the J psi down to the region of the rare channel. But that is a much easier thing to do than measure efficiency, absolute efficiencies.
Well, I don't want to flog a dead horse, but in the case of the J psi decay, you know precisely all the kinematics. When you're looking at K, E plus E minus,
yeah,
there's always a possibility there's additional unseen hadrons, like pi 0 or something like that. And if your Bremsstrahlung reconstruction of the electron is not precise, then maybe you include those in your E plus E minus sample, whereas of course that would not happen with a mu plus V minus sample.
Yeah, so I think that is checked by another test which I haven't included here, I'm sorry. We also measure the lepton universality at the J psi. So we measure B to K J psi EE over B to K J psi mu mu, right? So if we had spurious contribution to these would come different from 1, but it comes compatible with 1 at, I think, 1% level.
Okay, thank you.
Any other question? Maybe I will. Well, you have shown the Feynman diagrams for Z prime or leptoquark.
Yeah.
A very, very naive and general question. Experimentally, any hint if it is more preferable Z prime or leptoquark?
Well, at low energy, what we can do is to have several observables. As I mentioned, there's different decays. You can study angular analysis, so a lot of things, to get a handle on all the Wilson coefficient of the effective theory interpretation. And of course, different theories will give different contributions to these Wilson coefficients. So yeah, with good precision, there is a chance we can not only tell you there is an anomaly and we don't know what it is, we can also give guidance as to what are the preferred models that would fit that.
Okay, thank you. Any other question? Yes, please.
So you've talked about indirect searches for new physics. So any chances of direct searches for new physics?
Yeah. We have a number of direct searches for new physics. I mentioned the LACB was successful detector, and we extended our physics program and realized that there are searches we can do where we can be very sensitive because we are in the forward region of the LHC. Typically that means searching for particles that are very light, take a dark photon at 1 GeV, or heavy neutral leptons, or order of few GeV. That we can be very sensitive. We have a number of searches that place called best limits already, and this part of the program was really not foreseen when the detector was designed, and it's now booming.
Okay, thank you.
So, yeah, sorry for asking this one more time. What is the time scale of upgrading the RK anomalies?
Yeah.
Yeah. Standard question.
Yeah. So we have an upgrade detector installed, and this is starting to take data, but this, of course, will take a while to get measurements from the new data. However, we haven't measured everything we can measure in the data we have on tape already. So we've measured RK with the full data set, 9 inverse femtoband, but not RK star yet. And we are actually working on a combined measurement of these two, and additionally adding other Q-square bins, other Q-square regions. Yeah, and same goes for other channels, both in lepton universality tests and in B2K star mu and GR analysis.
Right. And
so time scale
results will be, I don't know, a few months or a few years?
Yeah, no, we are talking few months because we have the data set since 2019. But problem is that what's at stake at this point is, you know, we have a potential of a discovery, so that the collaboration is being extremely cautious, and the review is taking much longer than what it would take for any other analysis. So I think we have to be extra careful, and sorry we are letting you wait, but it's for the better.
Thank you. So, any other questions, please? Okay, then thanks again, Martino, for the nice talk. So it's time for a coffee break, and we resume at 11.
Oh, I just use that one.
Use this one.
Okay.
So I'll let you know at 5 minutes. So hello everyone. We can start the last session. So it's a pleasure to have Shufang Su from the University of Arizona. She's going to talk to us about precision Higgs physics, please.
Thank you. And I would like to thank the organizer for the invitation, and I'm glad to have this chance to share some perspective of the Higgs precision measurement, both at the current colliders, which is LHC, and the future colliders. So you hear me talking about mentioning all those future collider names. Okay, so yeah, time flies, and actually if you look back, I think we're 2 days away from the 10-year anniversary of the Higgs discovery announcement. So we are no longer just at the 5 sigma levels, and we are really, for the past 10 years, and in the future, we are entering into the precision Higgs era, and I will explain in detail what do I mean by the precision Higgs here. But on the other hand, if you look back at where we are right now, compared to like 20 years ago before the Higgs discovery, actually our wish list have not changed that much in terms of the new physics discoveries. Of course, discovery of the Higgs and the measurement of its properties is really wonderful because it helps us to exclude certain models. People no longer talk about technical models. And even for the other models, it helps to narrow down the parameter space because we do know we find a Higgs, which with this couplings almost look like standard models. So that helps to narrow down the parameter space. But on the other hand, other than the Higgs and a few of the 3 sigma kind of anomalies, the new physics, we haven't seen anything else. Okay, so that indicates either the new physics is getting heavier, or the coupling is weaker, or the background is huge. So we are getting a little bit of uncomfortable, I would say. But on the other hand, if you look at the big pictures, actually the big picture really haven't changed that much. We still believe there are still new physics beyond standard model, and we still try very, very hard to find them. So the question is, where is new physics? Maybe it's because it's heavier, maybe it's because the coupling is smaller, or maybe it's because the current the LHC, the background is just too huge. So there are 2 ways typically to looking for new physics beyond the standard models. One is, hey, let's just directly looking for the signatures of the new particles. We really want to find the new particles. And if the new particle is heavy, that typically means we need a machine with higher energy. So typically people talking about proton-proton colliders because that helps us to get us into higher center of mass energies. Or some of the E plus E minus machines like the linear colliders or the click, they can really get to the higher center of mass energy as well, or the muon colliders. Another way to looking for new physics is to measure the standard model particle properties really, really well. We have done that for the lab. We're looking for the Z's, and then now we can do the measurement for the W, for the Z, for the top, and if we have a Higgs factory, we can do that for the Higgs as well. So that typically requires a collider with a very, very clean environment. And the first thing, of course, that comes to mind is E plus E minus machines, because it's just such a clean environment. But on the other hand, if we have the PP machine with very, very high luminosity, if we have the hope to beat down the background, maybe that can act as a good indirect search as well. And as you will see in my talk, LHC can already do some of that. So my talk, will be focused on the indirect part. I'll skip the whole category of the direct searches. So this is where we are right now. LHC, we collect about 30 inverse fact bar at 7 to 8 TeVs, and we collect about almost 200 inverse fact bar at 13 TeVs, and right now we are entering into the round 3 stages, which hopefully will collect all the way up to 450 inverse fact bar over there. And as I mentioned, LHC is actually a Higgs factory because they actually produce way more Higgs than the Higgs that we are thinking of in the E plus E minus Higgs factories. If you think about that, LHCs with that much of luminosities can already produce 15 millions of the Higgs. And the usual E plus E minus, we're talking about 1 million of the Higgs. And the reason people kind of, even though we produce a lot, people really don't talk about LHC as a Higgs factory just because of the huge background hadronic environment. But otherwise, if you look at something which is statistically limited, then LHC is actually a good place to looking for those. And the high lumen LHC can increase another factor of 10 higher just because of the luminosities, and even the HH pairs, if you want to looking for the tri-Higgs couplings, we can actually have 120K. And this is something the low energy E plus E minus Higgs factory cannot do because they're really limited by the center mass energies, while LHC does not have that limitation over there. So let me kind of give you a global picture of where we are in terms of the current and the future colliders. And I separate that into PP and EE, and we like plots, so let's do plots. X-axis is center mass energy, and the y-axis is the luminosities. And this little almost invisible bar over there, that's the LHC 7A TeVs. So it's a lower center mass energy, not too much of the luminosities. And this is where the LHC run 2, run 3 will get to, so 13, 14 TeVs up to like a few hundred inverse fact bar over here. And this is where the high lumen LHC is, so where you get to the luminosity 10 times higher. And if you look at the future 100 TeV PP colliders people are talking about, you expand the center mass energy basically an order of magnitude higher. So help us to get to higher energies, and the machine I'm talking about for the future ones, there's a European version, which is the future circular collider, FCC-HH, Hadron collider, and the China version is the SPPC, the super proton-proton collider, but they are really talking about the same thing, a huge ring, 100 kilometers, get to proton-proton collisions, get to center mass energy 100 TeVs, and very high luminosities. So that's really like the energy frontier machine that we are talking about. Now let's go to the E plus E minus. This little bar almost invisible, that's where lab is. And this big blue one, you can see the center mass energy does not really go up that much, because to ideally produce a Higgs, the Higgs factory people usually talking about is a Higgs produced in association with a Z. So if you look at the cross sections, the best cross section actually gets to at center mass energy around the 240, 250 GeV. So lab kind of just missed it. Okay, so therefore you don't really need to aiming for a very high energy machines, but they are talking about luminosities almost like a 510 inverse fact bond over there. So the really high luminosities. And another version is, so that's basically go with the linear colliders. The particular one I draw over here is for the Japan version of the ROC. So because it's a linear collider, you can really get to higher center mass energies. But on the other hand, the luminosity goes opposite to the circular colliders. The luminosity actually is lower at the lower center mass energy, go up slightly for the higher center mass energy. So that's but typically the luminosity is lower than the Higgs factory that we're talking about. But on the other hand, it does have certain advantage when you go to higher center mass energy for the weak boson fusion process, which I will also mention. So the future E plus E minus collider, again, there's the European version of the FCC-EE, the Chinese version of the CEPC, and then this red one is the Japan version of the ROC. So whenever I talk about future collider, those are the ones that we have in mind. So let's back to the physics part. So now we have a light weakly coupled Higgs 125 GeV. The decay width is very, very narrow, and it's spin zero. It's a completely new kind of fundamental particles, unlike anything that we have seen before. It has no charge, it has no internal structures. Basically, it's just a neutral scalar. And one big problem for the neutral scalars that we knew even before the Higgs discoveries is nothing protects its mass. In principle, it could go all the way up to the Planck scale, but on the other hand, we have reason to believe they are around the electric scales. So even before the Higgs discoveries, there have been a lot of studies on the new physics beyond the standard model, just from the theoretical considerations, the naturalist problem, the hierarchy problems over there. So now we actually find it to be actually being light. It's basically strengthened these problems of what about its mass. Okay, so in terms of the theory side, let me just quantify that a little bit. So that's the usual Mexican head potential we talk about. It's being determined by two parameters, the mass parameter and the quartic couplings over there. And they can be replaced by the Higgs VAF, which we know 246 GeV. And they can also be replaced by the Higgs mass, which is 125. So basically, parameter-wise, we completely determined these two parameters. In particular, if you plug in the number for the lambda is about 1/8. Okay, so if you doing phenomenology like me, I'm happy with lambda being 1/8. But if you're talking to the more theoretically minded people, they will say, hey, what is the origin of lambda? We're just being uncomfortable of just plugging and putting a number as a potential instead of knowing the origin of this lambda over there. So people try very hard to find the origin of the lambda. So for example, in the supersymmetrical series, this lambda is actually related to the gauge couplings, which was cool. And there are other models that also. So we kind of want to understand the shape of this Mexican head potential. And another reason people want to do that is that when in Marcellus talk about the baryogenesis and things like that, to understand the Higgs potential will also help us to understand the baryogenesis and all those sort of stuff. And you might ask, is that we are happy with just one standard model Higgs, or maybe there's extended Higgs sectors. And ultimately, the stabilization of the electric scale is still there. By discover a light Higgs doesn't solve that problem, it actually make that problem even sharper. Why the Higgs mass is so light over here. So experimentally, of course, once we find a new particle, we want to measure its properties very, very well, its mass, its width, its spins, its CP properties, its couplings, because in the standard model, everything is basically determined. We know the mass of the particles, we know the Yukawa couplings. So but on the other hand, we do want to do the experimental measurement and to see if these two fit very well or not. And is there more than one Higgs? Are there other Higgses? So Sven talked about that in his talk. Does this Higgs just decay exactly as the standard model told it to? Or it can decay into something unexpected, like invisible decays, or decay into dark sectors, or other things over there? Now we have the Higgs. Can we use the Higgs to looking for other particles? And ultimately, where is the new physics? Where the so-called top partners to stabilize the Higgs potentials, and then where maybe it's connected to dark matter. So there are many more. But on the other hand, as I said, for my talk, I will mostly focus on the top part, the precision Higgs measurement. What's the current and the future status, and how we can use that to probe new physics beyond the standard models. But on the other hand, I think given the time, I might not go to the very end. But I have that on in my slides. If you're interested, you can check it out. Okay, so talk about precision measurements. For the past 10 years, experimentalists, they actually done a lot. We know much more about the Higgs compared to 10 years ago when we just have that two bumps over there. We actually know the mass very well. And we know the width also very well using these offshore techniques. And they did the measurement to compare different spins, different CP properties, and we kind of very sure it's a spin zero CP even particles over there. A lot of emphasis is on the Higgs couplings to measure the Higgs coupling to the various things. Some of them we did really well, like the Higgs coupling to the gauge bosons, and some of them, because of the environment, like Higgs goes to BB, it's still kind of messy. And in the early stage of in the first few years, the results are mostly presented in terms of so-called global fits, either in the Kappa framework or in the EFT framework. But nowadays, experimentalists, they actually did better. They actually present results, also the differential distributions, and also something so-called the simplified template cross-sections. So they're providing more detailed information of those distributions and the bin by bin kind of results for the theorist to interpret it. So I borrowed this slide from Ed Scott, which more to the left is kind of more model dependent, more assumptions. More to the right is kind of more towards the actual experimental data and things like that. And you can choose where you're comfortable to live in between. So since I'm a theorist, for most of the results I present will actually be in the Kappa framework or the signal strength, which is cross-section times branch ratio normalized to the standard model values. I will use most of that, but I do want to to emphasize there are a lot more results provided by the experimentalists if you want to look into it. So let's start with LHC. This product is a branching ratio, and we live on this red curve over here, which is a Higgs mass of 125. And you can see we are really being very fortunate to live in the region. Okay, before the Higgs discovery, it's unfortunate because that's actually the most difficult to looking for spot because none of the branching ratio dominates over there. But on the other hand, after the Higgs discovery, we are really fortunate because it gives a very rich branching ratio. We can looking for all those other channels over there. So you can see that the one I boxed out, those are the 5 major channels people use to looking for the standard model Higgs, the gamma-gamma, WWZZ, BB, and the tau-tau. The top 2 are the very earlier discoveries, and with more luminosities, people start to get into those. BB kind of still is difficult just because of the background, and but people are start to get into that. And also with the luminosities, people start to get into the suppressed branching ratio also, for example, Z gamma channels and the mu1 channels. So there are results coming out actually right now about those LHC latest results on that. So let me focus on a few of them. I'll focus on basically the mass, the width, the couplings, and and the HH, the tri-Higgs coupling, because that one is particularly interesting. So let me give you the status for the mass measurement. This is the current one, these 2. So you can see that the error bar is, I'll mostly focus on the error bars because we know the central value. The error bar for the current measurement is about 100 to 200 MeV over there. That's for the current one. And by the high lumen LHC, given the enhanced luminosities, you can actually reduce it to a factor of 10 smaller. So it's about 10 to 20 MeVs. And then for the E plus E minus factories, because of the extremely clean environment and because you can detect the Z on the other end, you actually don't really need to know what Higgs decay into. You don't use the usual Higgs decay final product invariant mass like LHC did. On the other hand, you can just use the recoil mass, just using the Z side of the information. Doesn't even care about what the Higgs decay into. You can do a very, very nice reconstruction of the Higgs mass down to 6 MeV over there. So you can see the precisions of the Higgs mass measurement. And you will say, hey, what can we use that for? So for example, in supersymmetric models, you can have a very nice prediction of the Higgs mass depending on the other parameters. So if we know the Higgs mass measurement really, really well, that would help you to constrain the parameter space as well. Next is the Higgs width. So the conventional way is basically looking at that little peak over there, be able to pull out the width information. That's what the so-called on-shell method. But you can see that they couldn't really do very well, especially at LHC, just because of the messy environment. And then later on, after the Higgs discoveries, people realized you actually can use some off-shell information. So look at the ratio of the on-shell, off-shell divided by the on-shells. And that one actually is proportional to the Higgs mass. And using this method, you can see they actually can get the Higgs width measurement really, really well. This is the current results. For example, the CMS, they can actually get to a central value, not just a upper limit. And with about few MeVs over there. And the standard model predicted the central value is 4.1 MeV. So you can see that we actually have a very good handle of the Higgs width right now. And for the high lumen LHC, you can further reduce the error bars by a factor of 2 smaller. And of course, everything is better, and not everything, most of the things are better at the E plus E minus Higgs factories. And they can really measure the width super, super well, down to 0.1 MeV over there. So that would heavily constrains any Higgs, any beyond the standard model Higgs scenarios, because, and in particular, the standard model Higgs decays, because if the Higgs decay into something exotic, that would increase the Higgs width. So if you measure the Higgs width really, really well, that will heavily constrain that one over there. So 0.1 MeV for the Higgs factories. And next, let me move on to the Higgs couplings. Before I give you the detailed results, let's actually step back and look at what kind of Higgs coupling we have. When you write down the Lagrangian, there's 3 parts involve Higgs. The first one is just the kinetic terms, which basically involve Higgs gauge couplings. So that part is not new. All the previous experiments we measured is about the gauge couplings, and the only thing is now we are doing the gauge coupling of the scalars instead of, you know, of the quarks and the leptons and things like that. So this is basically look at the gauge interaction part. This part is new because it only involved Higgs, that's Yukawa couplings. And the studies of the Yukawa coupling basically started since the Higgs discoveries a few years after, because the very first channel is a gamma-gamma and the ZZ. And so this part is completely new. It's the Higgs self-couplings. And I will say a few things about that. So far has not been detected. Okay, it's just being extremely difficult at LHC because of the messy environment. It's also very difficult at the Higgs factories because of the limit of the send-out mass energies, and I'll say something about that. So that's kind of what we're trying to measure in terms of the Higgs interaction. So now some results. The plots looks a little bit messy. Don't try to read all the numbers. I'll just tell you what's the highlights. So the left plot is basically the normalized signal strength, cross-section times branching ratio for each individual channels divided by the standard model values. But I'm kind of more used to the right one, which is the so-called kappa framework. You look at the couplings divided, you do a global fit. Then you look at the coupling divided out by the standard model's values over here. The central value is all something around the 1, which is good, which means we are consistent with the standard model Higgs. But the one I really want to pull out is the precisions. So this is at run 1. You can see that most of them is about 10 to 20%. That's what run 1 can do in terms of the Higgs couplings. And then this is the combined results for the current ones. You can see it's already much better than run 1. It's at few percent to 10% over there, okay? And this one is for the high lumen LHC. Again, let's focus on the right. So that's 2%, 4%. So you can see most of the coupling measurements. So the gray bars is including all the statistical, systematical, and the theoretical error bars over there. You can see most of the couplings we can get to 2%. Some is 4%, which are really, really well. Even at LHC, a high lumen LHC, you can already do percent level-ish kind of measurement. The one kind of it's a little bit sticking out is the muon. The muon branch ratio is just tiny. Okay, and also the Z gamma, the branch ratio is also tiny, and think about the Z decays. So these two, but still they're about 4 to 10% level over here. And these two are the ones which are pretty much statistically limited, which are given by this blue bar over here. The one thing I want to point out, if you look at all of them, the red bar are the theoretical errors. So you can see by the high lumen LHC error, most of the measurements are no longer limited on the experimental side. They are actually limited by the theory side for the theory precisions, if there's a way. And this is already a kind of predicted, not predicted, hoping for theoretical error over here. Okay, so let me actually spend one slides about theoretical uncertainties. Where do they come from? When you calculate the cross-sections, there are PDF that's wrapped in. There are uncertainty associated with the PDF. There are cross-sections, but those typically have QCD corrections, higher-order QCD corrections, so there are lots of effort on those perturbative QCD calculations over there. And then there are also those non-perturbative effects. And all three of them actually contribute to the theoretical error. So let me use the gluon fusion, the usual gluon fusion, as an example. So you can see that this is a scale dependence, which is goes into part of the perturbative and non-perturbative part. And this is a PDF kind of contributions, and this is strong coupling contributions, just because it's the QCD corrections over there. So lots and lots of work really need to enter into the theoretical contributions to reduce the theoretical error, because as I've shown in the previous slides, by the time of the high lumen LHC, for most of the coupling, the theoretical error uncertainty is actually becoming the dominating errors. Okay, so let's move on to the future ones. This is a typical projection cross-sections for the Higgs factories. E plus E minus goes to HCs. They'd be able to determine Higgs couplings really, really well, almost model independent. They can infer the Higgs total decay with really, really well, also model independent. And they can even probe some exotic Higgs decays or invisible decays. And this, I listed the CEPC, FCCE, and RLC. They are pretty much, most of the time, are kind of comparable to each other, especially for the CEPC and FCC. You can see that for the overall cross-sections, they can really get to a precisions of 0.5%. And if you translate that into the individual channels over there, and you can see they really get to like less than 1% level. And another thing I want to point out is this vertical ones. That's RC at 500 GeV. This new H is basically, it's not this plot. It's a E plus goes to new, E plus goes to another new with 2 W coming in. And the W boson fusion become a Higgs over there. So unlike the S channel, the cross-section goes down. The VBF channel, the cross-section goes up, and center mass energy goes up. So the advantage for those RLCs or the higher center mass energy click, for example, is that those VBF channel really kicks in. The cross-section is actually bigger than this dominant one over there, which help us to get very high precisions on certain couplings over here. So for example, if you look at WWH couplings, they can really get them better than the usual Higgs factories that we have over here. So here's just it's slightly outdated. People keep improving that. For the various carbons, you can see for most of the coupling, they are down to 1% level. And there's one which they can do really, really well, because that's the one associated with the production channels, the ZCH. They can really get to that, to the sub% levels. And yeah, people also did a lot of the EFT kind of global fit, and John Ellis here is definitely the expert on that. And so you can write down the Lagrangian as the usual standard model renormalizable interactions. Then you basically write down all the effective operators suppressed by the order of lambda square or even higher. And the dominant, the one I wrote down is just for the dimension 6. So they have become a standard tools when you deal with a large data set and when you want to do a global fit. The nice thing about that is a certain operator, they not only enter into the Higgs physics, they also enter into the electroweak precision measurement, they also enter into top quark, the top quark couplings over there, and all of them you can have a reasonably good measurement at current and the future colliders. So for example, this slides I borrow from area is so all those other ones, operators that could contribute to the Higgs. And for the yellows are the one to Higgs only, but for the kind of light bluish, those are the one could also enter electroweak measurement, and those on the red are the one could enter into the top. So you can really connect all the different measurements together and do a global fit and find out what are the limits on the C over lambda over there. So therefore you will see most of the results presented on the C lambda over square root C. So the top one is from John. And you can basically see that for the LHC, you can pretty much get to up to TeV levels over there for the various couplings over square root C. And that's it for the high Riemann LHC or the Higgs factories with the CEPC as a particular example, you can actually get to much higher. So that's a result in terms of the effective operators. Now let me get to the Higgs couplings, because that particular part is kind of interesting and a little bit unusual. So we kind of want to know what's the Higgs potential really look like. As Marcella mentioned in her talk, the Higgs potential really kind of related to the baryogenesis and things like that. So we kind of want to determine the shape of the Higgs potential. But on the other hand, it's not so easy to determine that one. That's the usual box diagram. That's the particular one involved the Higgs self-couplings over there, and they interfere, and unfortunately destructively. So for the LHC results, you can see that currently it has a wide range, okay, from -1 to 7, basically. And even at high Riemann LHC, say 95% confidence levels, you still have so 1 is the standard model value. So you still have about 50% uncertainties. And as a particle physicist, we're not happy with the 50%. Astronomers, maybe, okay? So the thing with the E plus E minus the Higgs factory is that if you want to have a Z, then Higgs goes to 2 Higgs. If you calculate the total center mass energy that you need about 500. So the usual E plus E minus machine of 240 GeVs really not give you too much approach about this tri-Higgs couplings over here. You kind of need to go to the RLCs and click where they have higher center mass energy to be able to give you a good handle of this tri-Higgs couplings. But those are kind of limited by the luminosities on the other hand. So you can see that even at those machines, they can really do well, about 10% 1%-ish, well, for those E plus E minus ones. The one that can really get to about 5%-ish is really a combination. It's really you go to those Hadron 100 TeV PP colliders and higher luminosities, so the statistics is not a problem. Hopefully you can beat down the background and things like that, then you can hopefully get on 5% level. But I would say this is probably the most difficult to measure Higgs couplings in the Higgs properties, and this is kind of, it's difficult, but on the other hand, we do want to have a good handle of that. So given the time, let me just flash some results. So far, basically all talking about standard model Higgs, how well we can measure it. But you can also use that to limit, constrain the new physics beyond the standard models, or even be able to distinguish new physics beyond standard models if in the future we find some deviations. Typical way of doing that is you take the experimental results of take the global fit results for the kappa, or take the global fit results of those FT operators, and then map into your favorite series. Or you can directly relate to the experimental observables of your new physics series as well. So there are various things you can do, and let me just flash a few results of my own work. And yeah, so this is the MSSM. X-axis is MA, Y-axis is tan beta. And the curve, so you can see, depending on where the stop mass is, you can 95% confidence level kind of curl out, allow the right part. And the one I want to emphasize is though the indirect measurement really plays a complementary role to the direct measurements. This is in the two Higgs doublet models. X-axis is cosine, the usual cosine beta minus alpha. Y-axis is tan beta. And the shaded region are the regions which is 95% allowed. And skip all the details. So the thing in the middle is what the Higgs factory can do. And the one on the most outside is the LHC row one. So you can see you can keep shrinking the premise space. So you can use that to distinguish new physics models, which I'll skip given the time. So to conclude, the discovery of a Higgs is really remarkable. And now we are entering into the Higgs precision measurement errors. A light weakly coupled Higgs, which is what current experiments are giving us, really argues for new physics beyond the standard models. And we can looking for new physics using both direct and indirect. And for the LHC run 2 and beyond, you can already do very well, better than at least I previously expected, given that it's a hadron machine, in terms of the mass with the coupling measurement. And the future colliders can certainly do better in terms of all the other couplings, except the Higgs self-couplings over there, and that's still kind of challenge. And as a theorist, given the experimental results, we can do a lot of wild things with it. Thank you.
Questions?
Very nice talk, Sofang. The Higgs self-coupling is one thing. What about the sign of mu square?
Sign of?
What about the sign of the mass of the Higgs? In the potential?
Okay. So, so that is kind of all related, because the actual measured Higgs mass is the physical Higgs mass after the electric symmetry breaking.
But how do you explain this sign?
And things like, so that you, okay, it's too much to flip back. It's a Mexican head potentials. So you really kind of, so the lambda is kind of, so the V and MH is kind of related to the lambda and the mu H over there. So what we know right now is after the electric symmetry breaking, which is where the MH is. So to note that, it's kind of more of a serious work, I would say, because for the experimentalists, all they can tell you is what's the value for the lambda, when they measure it. But when we have more, so if we have three, say we have V, we have MH, and we have lambda, that's more than the simplest Mexican head potential, which only have two parameters. You can certainly fit back, and that will hopefully give you some idea for the mu's. Yeah, but I would say that's more of a serious work to figure out what's the sign of this mu over there. Yeah.
One more question.
Sure.
Theory's problem.
Okay.
So you have to You have to look at the interference
Some
of your
interference
quarting or
effects.
trilinear with the other non-Higgs. I don't know, I have not done this analysis, but that's what I would do. Here you have only trilinear Higgs coupling. You have to have other processes with quadrilinear
Some
couplings.
interference effects.
And
to
then
figure
you have to make interference effects. I don't know how big these effects are, most probably very small.
Yeah,
But,
okay, thank you.
in principle, you could test your question.
Thank you.
Well, it's a question. It's we had yesterday in the Higgs session. We had a discussion about it. So this kappa framework is sort of a static framework. It's Q square Q independent framework. So
Yes.
it's like more or less like how is anapole moments or something.
Yes.
And so it suffers from gates. It's a non-gauge invariant framework.
That's
So
correct
it's
as
not,
well.
It's not a physical quantity. These are not physical quantities. So why we are resisting in just going through kappa framework and not the EFT framework, which is very well defined?
Yeah, the EFT is definitely more, I would say, theorists will prefer that because, you can impose all the gauge invariance, all the other things on it, but the kappa is kind of a more artificial thing. But I would say in the beginning when the experimental presented the results, say in terms of the cross-section times branch ratios, the most direct way to translate into the couplings is, hey, those are because they have the standard model couplings, you want to have the HWW, HZZ, so those are literally just the couplings over there. I would say it's out of convenience in the beginnings, but now we are getting more and more sophisticated. Of course, EFT is more satisfying. I agree with that.
Thank you.
Okay, if not, let's thank Sean again. Yes, I will show. This is and this. Okay. So our next speaker is Elena Caceres from the University of Texas at Austin, and she'll talk to us about the toy model of holography. So please.
Okay, so first of all, thank you very much for inviting me here. Let me check my time. Okay. And today I'm going to talk about this sparse SYK, wormholes, and chaos. It's related to holography, and this is work done with students at the University of Texas at Austin and publishing these two papers, and then there's preprint that will appear. Okay. Since this is holography, and let's set up the framework of this thing. It's ADS-CFT is this amazing connection between that tells us that the D-dimensional conformal field theory is completely equivalent to a gravity theory, but in a different space, right? In a D+1 ADS space. So this is exemplified here by saying the red thing is the boundary, is where my quantum field theory lives. And that is exactly equivalent to a gravity theory in this internal space with the angels and demons. Okay. And the angels and demons are there. Is that good? Yes? The angels and demons are there to remind us that this is not flat space. This is anti-de Sitter space. It's a negatively curved space. So in flat space, if we will measure the size of these angels and demons, you will say, oh, the ones in the middle, they are larger than the ones towards the boundary. But in ADS, because it's negatively curved, all these angels and demons have the same size. It's just to remind us that it's a different space, right? And this thing that you always see that is like the logo of ADS-CFT, it's a T0 slice, constant time slice of the whole space. The whole space will have time going up like this, and this whole thing is just a slice. So the idea is that our quantum field theory lives in the boundary, and it's equivalent. Somehow there is a relation between, there's a mapping between this quantum field theory at the boundary and gravity in the bulk, what we call the bulk. Okay, so then the whole thing is that ADS-TFT geometrizes quantum concepts. What was the quantum concept in the boundary, it turns out we have to calculate, since these things are equivalent, we have a dictionary that the community built for many years, and in order to calculate some quantum things at the boundary, we have to calculate some geometrical things in the bulk. One of the quantities that has been like most successful in the last years is the holographic entanglement entropy, and you will hear Yuta Kayanagi or HRT, Hubeni, Rangamanita Kayanagi. And the idea is that to calculate the entanglement entropy at the boundary of a strongly coupled field theory, which is something very hard to calculate, that is reduced through this duality to just calculate a minimal area in that bulk. And that's a classical problem. So it's much easier, something that's totally quantum in the boundary, we just transform it into its equivalent to some semi-classical calculation in the bulk. Well, and this has been hugely successful, and it opened up the door also to understanding that there are other concepts like complexity, for example. If we want to understand what's behind the black hole horizon, then we have to ask for what is the complexity, and all in all this area points to the language of quantum information is really important to understand this duality. Well, so I have been working like for the last 10 years in this area, like kind of, it's very connected to GR. But the main question here is how really are the quantum degrees of freedom encoded in gravity? That is something that we do not really know exactly. How does this happen, that the theory at the boundary is completely quantum without gravity, and that is supposed to be equivalent to a gravity theory in a different space? What is precisely that encoding? That's what we're trying to find out. But one hurdle that we face is that going to the other side, so we don't have a quantum model. It would be nice to have, well, we have one, and that's what I'm going to talk about, but we don't have many quantum models that we will say, this quantum model has exactly a gravity dual. I mean, we have some quantum field theories, like say, like N equal 4 super mills and stuff, but we will want a quantum model that is solvable, right? Something that we can solve and say, oh, this one has a gravity dual. And so we can see the black hole physics that is predicted by this duality appearing in this quantum model that is solvable, right? So we don't have many of those. Essentially, the only one is this one that is called SUSY-2022 model that was proposed, but it's called SYK, and this is from 2015. And but we will want to have more, right? I mean, it would be better. So recently, Xu, Susskind, and Swingle proposed a new class of models that are called sparse SYK, that they have many like, they are more computationally efficient. And because they are computationally efficient, we can do numerical simulations, because this other one, as I'm going to tell you in a second, it's very hard to do computational simulations for large N, finite but large N. So in this talk, I want to tell you what is the sparse SYK and show you some results. That's essentially what we're going to do. So that was kind of my introduction, and now I will tell you what's the SYK and the sparse SYK. Then we will see two coupled sparse SYK, which are supposed to be dual to a traversable wormhole, and then other phenomenon that is called revivals, the spectral form factor, and then future directions. Okay, so what is the SYK model, or all-to-all? So this is the original SYK, not the sparse one. What is this original model? Well, it's a quantum mechanical model of N Majorana fermions. Fermions here, it's a Q-body interaction. So Q can be any even number, but it's a Q-body interaction. Mostly we do 4 and 8, okay? And the thing is that the couplings here are Gaussian, random Gaussian couplings. So they have all random interactions drawn from some Gaussian distribution with zero mean and variance given by this expression. This J here is the parameter that fixes the energy scale of the model. So this model has been shown to be completely solvable when n goes to infinity. Okay. And it has an emergent conformal symmetry at low energies, and it's maximally chaotic. All this was shown in 2015 or something. So then this is our toy model for holography. When we are in this limit of beta j much larger than 1, so this is the very low energy limits of the model, this has a gravity dual. We know what the gravity dual is, and it's called Jekiv-Teitelbaum gravity. There are generalizations of this model, the charge SYK, the supersymmetric SYK, but they all are kind of have the same structure. Now, as I said, this model is completely solvable when n goes to infinity. But if you want to see how gravity, how this model at n going to infinity and in this limit, I know that it has a holographic dual. But if I want to do finite n calculations to see how it becomes a model with a gravity dual and understand the physics at finite n, then I have to do numerical simulations. And that's a problem, because of the randomness of this model, the number of terms goes like n choose q, and that for large n is like n to the q. So to give you an idea, for n equal 52 Majorana fermions, we will have around 7 million terms in the Hamiltonian. So doing numerical simulations for a Hamiltonian with 7 million terms is pretty difficult. So the state of the art is like n equal 52, and people cannot do more. Okay. So then the question that some people started asking is there a modification of the SYK that will retain all the interest in physics, but that will be more computationally efficient? And that's when the sparse SYK comes up. So that's the sparse SYK. So the sparsity means that we reduce the numbers of terms in the Hamiltonian. But we try to preserve the original properties, that is chaotic and that it has a gravity dual and all that. This was proposed by Xu, Susskind, Xu, and Swingle in 2020. And there are two ways of introducing the sparseness: random pruning and hypergraphs. So random pruning is more intuitive. So this is our original, if you remember, this is our original SYK, and now I have introduced these X's. These H's are the Majorana fermions, but now I have these X's here. And so I'm going to just prune some terms. So I'm going to delete some terms. This is a random Hamiltonian. So I'm just going to delete some terms with certain probability. So these X's are 0 with probability 1 minus p and 1 with probability p. Okay, so I just delete some terms. Of course, if this p is 1/2 or 1/4 or 1/3, then I have not done much, because from n to the q, I'm like 1/2 n to the q is not that much. But I'm interested in when this probability is really, really small, in such a way that the number of terms is reduced to be linear in n. So I want the Hamiltonian to have just kn terms, where k is an order of one number. Okay. So then I should have n choose q was the original number of in the SYK times the probability should be k times n. So this probability, as you see, has to be very small. If I do that, then for n equal 52 with k equal 4, now I have 208 terms. So that's much more doable. We can calculate things here. So we can do numerical simulations at higher n, and also for higher q, because with the original SYK doing higher q, so q equals 8 and stuff, it's very difficult. Okay, and then Susskind and Swingle and all them, they also show that there's a path interformulation, it preserves chaos, all that. But one question is, how sparse can this model be and still preserve all the physical quantities? And so essentially, what is this value? How low can I push this k, right? And still have all the physics that I want. And then now, let's say I have this new framework. Let's say I have this sparse YK that is supposed to behave very well and stuff. Can I find something new, something that I couldn't find with numerical simulations in the original SYK because of numerical limitations, right? Okay. So in order to look at that, look at how sparse the model can be, a very useful language is hypergraphs. Now, I'm going to skip all the math of the hypergraphs that we use in the papers. I'm just going to give you the main idea of what hypergraphs is, and then if you want to see all the equations. Oops, what happened here? Somehow I went like, okay, I think we were here. Yes, useful language is hypergraphs. Okay, so a hypergraph is, probably we all have an idea of what a graph is. A hypergraph is a generalization of a graph, but where the hyperedges can contain more than 2 vertices. Now, this idea of hypergraphs is being used in many things, right? It's a mathematical abstract formulation that can be used for many things. For example, people that have models and how fake news propagate using hypergraphs, or epidemiologists also use hypergraphs, or even in neuroscience, in many areas, hypergraphs can be used. What we want to do, what we do here, well, let me show you a little bit what hypergraph is. So this is a graph. Mathematically, a graph is just defined as these two sets of vertices and edges, okay, such a way that an edge always connects 2 vertices. So E are the edges, and they will always connect 2 vertices. So this is the set of edges, and the cardinality of that set is 2. So it will always connect pairs of vertices. Okay. A hypergraph, now the edges can connect more than 2 vertices. By definition, they connect more than 2 vertices. So it's the same idea that it's one set of vertices, one set of edges, but now the edges have cardinality larger than 2. Okay. Now, this is just a good like, I'm just showing you a picture to have an idea, but mathematically, this is really a branch of set theory, and there are many rigorous results in math related to hypergraphs. Not as many as the ones for graph. For graph theory is an old branch in math, and there's a very well-established whole set of results. Hypergraph is recently new. Like, some of the results we use are from 2019 in math. Well, so what about hypergraphs? We want to realize the sparse SYK as a random hypergraph. So that Hamiltonian is going to be you can see how, okay. Now, what we want to do is now each term in Hamiltonian is going to be one edge of a hypergraph that connects, let's say, 4 vertices. Each Majorana is going to be one vertex, and an edge is each term in the Hamiltonian is going to be one edge in the hypergraph. Okay. So the Majorana are identified with the vertices, and each interaction term, so a term in the Hamiltonian, corresponds to a hyperedge connecting Q vertices. So it's Q uniform. We want each hyperedge to always connect Q in the case that I will show you, 4 or 8, 4 vertices. So like that, I can translate my Hamiltonian in realize, as people say, realize the Hamiltonian as a hypergraph. Okay. And, okay, K was this parameter that quantified the sparsity in the Hamiltonian. Now, and so we define this sparse Hamiltonian as the sum of K and the sparse Hamiltonian will be a sum of just Kn terms. Remember that we want to define this K, okay? And I will skip the math, but then that means that we're going to be interested in random regular hypergraphs that are also characterized by this K and Q. Q, remember, Q is the number of Majoranas that interact, so it can be 4 or it can be 8, whatever. And K is the parameter that tells me how sparse the Hamiltonian can be. So we're going to realize this Hamiltonian in random regular hypergraphs with these two parameters, K and Q. Okay. And fortunately, the mathematicians have results about what we want is hypergraphs that are highly connected. Because one of the features of this SYK and sparse SYK, one of the things we have to have in order to have a gravity dual is this Hamiltonian has to be chaotic, has to be maximally chaotic. In order to have that, this sparse hypergraph has to be highly connected. Okay, and those hypergraphs are called expanders in the math literature. And so we can study measures of connectivity, of hypergraph connectivity. And so here's where I skipped several slides. I will not show you the algebraic hypergraph entropy, vertex expansion, spectral, but there are measures of connectivity that the mathematicians have studied that then I can translate to my Hamiltonian and study it for my case in order to determine what is the optimal K. Remember, one of the questions was, how much sparsity can I have? And what I'm trying to tell you here is that I can, by translating this Hamiltonian to the language of hypergraphs, then I can use math results for hypergraphs in order to study expander hypergraphs and to determine how much sparseness can I have for each Q. Okay, so if somebody wants, we can talk more about where does this come from and what are these measures, but bottom line is that when I have a Hamiltonian that has Q4 Majoranas interacting, I can have K equals 4 is a good measure, good sparseness. And if I have Q equals 8, then K equals 2 is good. And that makes sense, right? Because if my Hamiltonian, each Hamiltonian has 8 Majoranas interacting, then I can get away with a lower K, right? Okay. So now that we have that, this is all from math formulation of hypergraphs and all that. So then I have to ask, so does this really reproduce the physics that it's supposed to if it has a gravity dual, right? So one of the things that we can test is for the old SYK, there was a formulation about how to construct a traversable wormhole using sparse SYK. And we will see now, so what I want to test now is if with this sparse SYK, it does reproduce the physics expected of a traversable wormhole, okay? So let's remember that we are talking in ADS spaces, and in particular, this will be in ADS2 geometry. Since this is just a quantum mechanical system, it's going to be dual to ADS2. Okay, so the eternal traversable wormhole with a global ADS2 geometry can be realized by 2 copies of SYK. So this is the original SYK. Imagine I have just 2 independent copies, 1 copy of SYK in each boundary. They don't talk to each other, so there's no way to go from one to the other. So this is non-traversable. But if I couple these two, the SYK left and the SYK right, like with this interaction term, right, then the geometry becomes traversable. And this was shown some time ago. This is a mechanism discovered by Gao, Jeffries, and Wall, 2016. And this solution can be obtained from gravity by adding some couplings between the boundaries. This is a beautiful story, but it's all GR. And you can see that the wormhole opens a little bit, and then the wormhole becomes traversable. That's from the GR side. The dual side, the quantum mechanical side, was studied by Maldacena and Xi, and it's essentially you have your SYK left, you have your SYK right. If it was just this thing, your Hamiltonian, then your dual will not be traversable, but you add this interaction where you couple 1 Majorana from the left and 1 Majorana from the right, And that reproduces the physics of these traversable wormholes. Okay. So now, since my whole thing is I want to study the sparse SYKs because these are computationally more efficient, right? And so then, if these sparse SYKs are really giving me the physics of a gravity dual, they should be able to reproduce whatever I expect from gravity in this case. So then I will study two coupled sparse SYKs. And, oops, sorry. And this is essentially the bottom line. I'm not going to go into the details, but what is this telling me? In this axis, I have mu. Mu was the here. Yes. Oh, sorry, I'm not sure what's going on with this thing. Okay, here. Properties of the two coupled SYK models. So I have this thing. So the ground state is approximately a thermofield doubles for some temperature, okay, whatever. But the main characteristic, when can I say that this is a gravitational result? So this is a result obtained purely from gravity. And the energy gap scaling of the system should go like this coupling, that like this mu to certain power at weak coupling. The power depends on Q. Q is the number of Majoranas that I have. So it could be 4 or 8, whatever, right? So at weak couplings, when this mu is small, the energy gap should scale like this. In our case, that would be 4/7 or some weird number, depending on which Q. And strong coupling, it should be linear. So this is the prediction from a calculation in gravity. The idea is that if my quantum model really has a gravitational dual, it should reproduce that prediction for just calculating the energy gap of the system, right, of the quantum mechanical system. Oh, wow, okay. So here it is. This is for Q equals 8, K equals 2. The different colors are different ends, so different number of Majoranas. And this dashed line here is the one that has the scaling to the 4/7 or whatever. It's the 1 to the mu to this weird power. And the dotted is the linear. And we can see exactly that it follows the expected behavior from gravity. So this model is behaving as a traversable wormhole in the dual geometry. In this part, obviously, that's not working, but this is probably finite n effects. I don't know. But this part, this scaling is working perfectly as what we expected from gravity. Okay. So that was for Q equals 8. For Q equals 4, matches the perfectly scaling for large n. Finite n effects dominate a very small coupling, and that's what we see. Okay, so we have our traversable wormholes in the sparse SYK. There's a phenomena called revivals also. I might skip this because I'm short of time, but revivals is just a well-established phenomena in chaotic systems, in quantum chaotic systems. And the idea is that you create a Majorana on the right-hand system, a right-hand Majorana, but because it's chaotic, the excitation gets scrambled, and then it reassembles after a certain time on the left. Okay? And the process is repeated left, right, left, right. This is the well-known physics of quantum chaos in this type of systems. And so there's these revival oscillations. In the gravity picture, this means that the perturbation is traveling through the wormhole from the right to the left and then coming back and forth. Okay? So we should be able to also see this physics that is well known from the quantum system. I mean, this physics is the perturbation traveling through a wormhole. We should be able to see it in our sparse SYK also. For that, I have to define a transmission amplitudes. These are just Green's functions, left, 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 right, right, left, etc., all the combinations. And say TL right squared is the probability of recovering the left Majorana after some time that you insert the right Majorana. So you insert the right Majorana, and after some time you recover the left one. That's the probability that the signal has gone through the wormhole or that it has reassembled in the quantum mechanical system, it has reassembled on the other side. And the typical thing of this, this signal is that it should be like oscillating, like this. These are results from another paper, but this is essentially what we would want to get, is T left left and T left right, T left left and T left right, they alternate, right? One has a peak and then the other one has the bottom and then it gets to the other end and then comes back and like that, right? So this is probability of that the signal is going through. So this is essentially what we would, oops, what happened? And this is just the dependence on the coupling, how depending on the coupling. And this is what we want to see with our sparse SYK. And yes, we do see these oscillations. The frequency of these oscillations is important. It's related to the scaling of that energy gap also, and we can also check that the frequency of the oscillations is correct. So we have traversable wormholes and we have revivals in the sparse SYK. This I have to mention, this was done in the supercomputer in Texas with something called the Dynamite program that does the parallelization, and it was my students that did all the numerics, but yeah, we did that. So then right now I have shown you that we can see things that we expected, essentially. We expected a traversable wormhole, we can confirm the traversable wormhole. We expected the revivals, we can see the revivals. Can we see something new? And then I'm going to be fast on this thing, but the new thing that we can see is related to a measure of chaos that is called here, the spectral form factor. Well, let me see. Yes, random matrix theory provides the diagnostic of quantum chaos, and let's start here. The out-of-time order correlators are a measure of quantum chaos, as is random matrix theory. Okay, and a quantity that is sensitive to the energy level statistics that we need in order to see if something is chaotic or not is the spectral form factor. The spectral form factor is just defined like this. This is just the partition function with some analytic continuation, and this is the quantity we're interested in. It has a disconnected part when I just have z times z, and it has a connected part, which is the total minus the disconnected. Okay, so the whole point is that in 2015 or 16, people did this for the SYK, and they found this spectral form factor, which is very interesting from the gravity side because it tells me here it's disconnected, and here this part is the connected. It's like a wormhole. Okay, but the idea was that it was always will be the disconnected dominating up to a certain time, and then the connected will start dominating. What we can see now with the sparse SYK, because we can do numerical simulations with higher n, I will skip this, skip that, is that there is a dominance of the connected much earlier than the deep time. So this was the deep time, and before what we knew is that it will connect, it would be the connected part will dominate from here. This is the wormhole phase. And now we can see that there's a contribution of the connected part that dominates much earlier on. So, okay, and this was possibly to do because of the sparse model allow me to do numerical simulations that were before. We would have needed like n equals 60 for the SYK, and nobody can do that for the spectral form factor. Okay, the Lyapunov exponent, I'm also working, I think I'm running out of time, so we also can extract the Lyapunov exponent. And then for future directions, just like I can explore the traversable wormhole and signal is going back and forth, there's another measure that was recently proposed to study collisions behind the horizon. So how can I detect from my little quantum model when in the gravity dual I send two signals and they collide, but they collide behind the horizon? What quantity in the quantum model can detect that? And it is this 6-point function. So yes, that's something that I want to look into this sparse SYK. There's very recently proposed a certain limit of this sparse SYK that is supposed to be dual to de Sitter. I do not know much about that, and there are many things to be done. So, okay, thank you. That's it.
Other questions?
Okay, thank you for your talk. Probably you said, but are you assuming any special geometry for DIM+1, ADS or something, or?
Yeah, so the SYK is like what they call it is like near ADS2. So it's a low energy thing that at low energy, so at certain distances, it looks like ADS2, but in the boundary, it can be a little bit deformed. It can be a bit near ADS2.
So can you check something else as DS, for instance, or I don't know?
Well, a lot of work has been done in the last years, just working a lot with ADS. And there's a whole formulation and path integral, and everything works really fine. And we're very excited because that is a toy model that we can actually see how this encoding of gravity works in the degrees of freedom, because we have two sites under control. Very recently, it has been proposed a certain limit of this model that is supposed to be dual to de Sitter. But that's a proposal by Susskind of maybe few months ago, so it's not clear yet how will that work.
Okay, thanks.
You mentioned at some point in algebraic entropy of hypersurfaces, hypergraphs,
yes,
sorry.
Yeah.
Could you say a few words about how you define?
Yes, definitely. I have my slides here. So hypergraphs are really cool. It's a really cool branch of math. And it all depends on this thing that is called the adjacency matrix. So since the hypergraphs, you have your vertices and stuff, for every hypergraph you have, whatever hypergraph you have, you can define its adjacency matrix, okay? And it's just a question of saying, like, each element here, the number of hyperedges containing an adj, and 0 if they're the same, okay? This adjacency matrix contains all the information about the connectivity of the hypergraph. And so, for example, what you were asking me, the algebraic hypergraph entropy is defined. You see, this is the adjacency matrix, and this is just some operator that the mathematicians have come up with. This is just some diagonal matrix that if you have the adjacency matrix, you can just define this diagonal matrix, the sum of the elements. So you define this operator, D minus AH, this is the adjacency matrix, and the eigenvalues of this, nu I log nu I, that's the algebraic hypergraph entropy. So it's just completely, it all boils down to, given a hypergraph, you determine its adjacency matrix, and from there you can get the information that you want.
So the next speaker is Hello, can you hear us?
Yes, yes, I can hear you. Can you hear me? Yes. Shall I start share my slide? Yeah. Can you see? I can put full screen.
So it's a pleasure to have this talk by Gino Isidori from University of Zurich. So please.
Yeah, thank you. I'm really sorry not to be there. I mean, it is Corona is really tricky. I mean, I survived for 2 years, but finally I got it 2 weeks ago. Anyway, it's a thank you for accommodating the talk online. So my plan is to discuss about some new ideas about unification, because this is a conference about unification, not only supersymmetry, which are inspired by flavor physics. So this is the plan of the talk. I'm switching slide. Do you see a new slide? Just to be sure, because sometimes it doesn't work. Okay. So, these days we are celebrating the 10th anniversary of the Higgs discovery, so the completion of the standard model spectrum. But I think that, honestly, this is, of course, it's beautiful, it's very nice, but I think we always been thinking that the standard model is only an effective theory, right? The fact that we have completed the spectrum is, in a sense, is just the first step to understand what's beyond. And what we understood is that in this effective theory, there is a mass gap. So clearly there is a nice part of the a well-defined part of the spectrum which complete with the top, which is actually the heaviest state. But we think that this is only the long-range result of a more general theory which contains more degrees of freedom. And we would like to understand what is this theory behind. And so ideally, we would really like to go to higher energies to understand which is the ultraviolet completion of the standard model. But of course, as you know, this will not be possible for the next 30 years. And so what we can do right now and for the next several years is to do more indirect tests of this effective theory and try to explore information about the UV looking at the infrared. And what we can see, I mean, looking at the structure of this effective theory is that, especially in the low energy side, there are a lot of properties which are peculiar. Now, we have a lot of tunings in the couplings, especially concerning flavor couplings, and a lot of accidental symmetry. And exploring better this sector, I think it's really a very powerful tool to understand something in the UV. And we know this generically in effective theories. You know, when we look at an effective theory, the accidental symmetries are very interesting because these are symmetries which we think are not fundamental properties of the underlying theory. So we think these are symmetries which are not valid in the ultraviolet, but they arise accidentally in the low energy limit simply because we don't have enough variable to describe the violation of symmetry. So the local interaction, the long distance interaction, which are the dimension 4 operator, cannot describe the violation of a symmetry. But if the symmetry is violated at some high energy scale, then, then this effect should be visible, suppressed by looking at higher dimensional operators. So the higher dimensional operator are the only one that can describe the violation of accidental symmetry. And this is a very general properties, I mean, true in all effective theories, that we have enhanced symmetry at low energy, and there's testing this enhanced symmetry, we can hopefully have information about the UV where the symmetry is not valid. We have seen many interesting examples in the past, I mean, even the Fermi theory itself, the discovery of the charm were all of this type. But what is interesting these days is that the hint of lepton flavor universality violation, which seem to be present in B physics, are exactly of this type. And this is what I want to discuss. So let's now give a very brief look to the data. There was already a very nice talk this morning by Martino Borsato on the so-called B anomalies. So I will be very brief just to take the message which are important for the rest of the talk. So as you know, since 2013, it's already really a long story, result in selectronic B decays started to exhibit some tension with the standard prediction, connected, I mean, at least some of them, to a possible violation of lepton flavor universality. So more precisely, we seem to observe a different behavior between muons and electron in B2 SLL, and a different behavior of taus versus mu and electron in B2 charge current, B2 charge lepton neutrino current. So what is this lepton flavor universality? Well, lepton flavor universality is indeed one of these accidental symmetries of the standard model Lagrangian. Actually, it's not even an exact accidental symmetries, is a symmetry which is approximate and is valid in the limit where we neglect the lepton-Yukawa coupling. You know, the lepton-Yukawa coupling that I report here are all very small. Even the tau-Yukawa coupling is 10 to minus 2, so it's much smaller than any of the gauge coupling. So it's usually a very good approximation to neglect this Yukawa coupling. This is what we do when we evaluate transition probability. So we typically retain the lepton Yukawa coupling only for free space effect. And this is what we think is a very good approximation in the standard model. And this is what gives rise to this approximate universality. But you see clearly there is nothing deep in lepton flavor universality, in lepton universality in general, because it's just an approximate fact which is stick to the dimension 4 structure of the standard model. So it's likely to be only an accidental symmetry which is violated at high energy. Indeed, it's already violated in the standard model, but in the only sector which violated in the standard model is a sector that contains a small coupling. So maybe if there are different sectors, this violation could be bigger. So just a slide to show all the hint of anomalies in B2S mu, and what is striking here is that we have a lot of different observable, all connected to something which indeed could be a new point-like B2S mu interaction. Now, there are these very nice LFU ratios that Martino described. So this decays of a B hadron into a hadron containing the strange quark, and the muon pair normalized to the electron pair. And here we see a lot of deviation. None of them is strikingly significant. Okay, here there is a 3 sigma one, but it's the pattern that it's interesting. I mean, and of course one can average these things. I mean, the LSEB don't do it, but I think we, the theoreticians, like to do it because we think it's really measure the same thing at the shared distance level. So here there is a interesting high significance. This is very clean theoretically. It's very difficult experimentally, very clean theoretically. Then there is BS mu, where we also see some deviation. I mean, in a suppression of the experimental result compared to the theoretical prediction. Here, the prediction is very precise. The significance is not that high. So here, the significance is not high, but it's nice that there are other experiments involved. And finally, here there is a high significance in processes that involve mu1 only, or this B2K mu angular distribution of the branch ratio. Here, however, there is more theoretical uncertainty because here the form factor uncertainty, the long distance effect are not completely under control, but to the best of our knowledge, there is a tension there. So just to be the devil advocate, of course, there are problems in all of these. Here, if you want, it's only an experimental problem, but there is only one experiment involved. Here, as I said, there is low statistics, and here we have non-negligible errors, but the overall picture is really interesting. This is why I think it's, I think, honestly, I've not seen anything of this type in the last 20 years. Okay. Then there is the other sector that are the charged current anomalies. Here the situation is much less clear. If you want, we have much less evidence. Still, it's nice because it's the same type of phenomenon in a sense, which is a observation of larger number of taus with respect to light leptons in process of the type B2 charm. And the result here, even if they appear to be scattered, are very consistent. It's a 30% probability of consistency among the experimental results. And when you average them, you see a 3 sigma deviation with respect to the standard model. So again, it's nothing striking, but again, interesting and exactly of the same type, but with different leptons and quarks involved. So these anomalies are seen only in semi-electronic operators. With definitely something connected to, if you really want to interpret as an evidence of something new, it has to involve left-handed field. And it's nice because when you have a left-handed field, you naturally have a connection between neutral current and charged current. And what we seem to see is something large competing with the standard model at 3 level in B2 charm, tau, neutrino, and something much smaller, but possibly cleaner theoretically in B2S muons. You see here we have more second generation field, here we have more third generation field. This was, for me, really the starting point to try to put these two things together because it's a very nice flavor structure, okay? So it's something that can be possibly large for third generation and smaller for the second generation, or eventually even third generation that we have not seen yet anything. And so it naturally points to a link to the pattern of U-kappa coupling that we see in the standard model, which is very nice. So it's not only a set of anomalies, but it's a set of anomalies which exhibit a pattern that it's meaningful. So more precisely, if you really want to understand the size of deviation that we see, so the biggest anomaly is the one that we identify with the highest significance is this B2S mu operator, a purely left-handed operator of this type, which now I write in general terms. So as you will see, all the anomalies can be described by operator of this type, quark, lepton, lepton, quark, with specific flavor. So the one for which we have the highest significance is this one, 2, 3 mu, where 2 and 3 refer to the quark, so it's second and third generation. And then the muons, of course, refer to the muons. This is the one that predicts this left-handed shift, and the size of the effect is small. You see, it's roughly 10 to minus 4, 10 to minus 5, the Fermi coupling. So it's a typical super weak interaction. So something naturally to be expected if this symmetry is not a fundamental symmetry in the UV. And it's a clean effect of short distance energy. And you see this is, I plotted here in this plane where you have this delta C9 equal minus delta C10. This is the standard model, and this is what the data tell us, using only the clean observable, so those with no theoretical uncertainties. Then we can have, we can put also in the game the observable which are more dirty. In this case, what we seem to observe is also a universal shift to both electron and muons, controlled by this parameter delta C9 universal, which is something that we can describe again by the same operators here assume that there is a bigger effect for taus, which is consistent with this idea that effects intergeneration are bigger. But then if you have a bigger coupling here for taus, and you close the tau loop with the photon, you generate a universal correction, same deviation from mu and the electron. This seems to be present in the data. So indeed, the best fit of the data of all these B2SLL data is a fit with two parameters, this universal shift and this non-universal shift that involve only muons. And the two set of data agree quite well. Of course, the errors are still large, but there is a nice consistency. Note that, of course, the errors are large, so if the deviation changed by a factor of 2, nothing changed really, but the overall size is fixed. And the size is such that this 2,3 tau tau has to be 100 times bigger than the effect we see in the 2,3 mu mu. So it's indeed here normalized by 10 to the 3, here normalized by 10. So there is a 2 order of magnitude difference. And this means that if we have third generation field compared to second generation field, we have to pay 10 to minus 1 suppression. Now, what is really nice of this is that actually this type of operator was already identified before we saw this effect in B2SLL from the other anomalies, from the charged current anomalies. So the size and the necessity of this 2,3 tau tau was predicted from charged current, okay, before this effect was observed in neutral current. So it's a very nice consistency of the two type of anomalies. So let me now look at the charged current. So in the charged current, again, the same type of operator can describe perfectly the data. Now here, one has to be careful because, so in the charged current, we see a B to charm transition. So in this case, we have an up quark, okay? So here I choose a basis where my reference index for the flavor are the down quark. So I can have two contributions, either a 3,3 tau tau, which means a BB tau tau, and then I have to pay a VCB, a CKM rotation, or I can have a B2S, and then I have to pay a VCS factor. So it's a combination of these two things that we don't know the relative weight. And so it's a band in this plane where I put now the coupling 3,3 tau tau and 2,3 tau tau. You see, this 2,3 tau tau was the one that already identified from B2SLL. And so here is a band. I cannot go more than here because otherwise I have bound from direct searches on the BB2 tau tau operator. And finally here I can put the information that I had from the other observables, and you see the nice consistency of all these anomalies. So there is a nice consistency between charged current and neutral current anomaly, all described by this type of operator with the precise scaling. So there is the biggest effect is the 3,3 tau tau, so BB tau tau. This is the biggest coupling. Now, this is in units of the Fermi coupling is 10 to minus 2. Then I have to pay a 10 to minus 1 suppression if I replace a B and go to an S quark. And then I have to pay 10 to minus 3 suppression if I go to this 2,3 mu mu operator. So if I replace the 2 taus with 2 muons and the B with the S. So it really seems that each time I put a second generation field instead of a third generation field, I pay 10 to minus 1 suppression. So I think it's a very nice, again, interesting picture. So let me try to summarize because probably, I said too many things. Let me try to see this from which is the main information. The main information is that we think, I think if you want to interpret this data, that there is a relatively big effect involving intergeneration controlled by a scale which is actually it's quite close. It's few TV, okay? And then each time I replace a third generation, I go to second generation, I pay 10 to minus 1 suppression. So if I go up to here, BS mu mu, I pay 10 to minus 3. This actually is the effect, the most significant effect, the one we see in B2SLL, controlled by this R ratio. But then these other things, we see it also because the B2S tau tau is the one that when you close the tau loop also is visible with less significance, but still is visible in B2SLL in a consistent form with this scaling. And then these two, once you take into account the CKM rotation, contribute to B2 sharp to the RD anomalies, which is a 3 sigma. So it's a very nice, consistent picture. Of course, one should expect at some point to see B2S tau mu with this strength, and the fact that we have not seen it yet is consistent because it's a very difficult measurement. And finally, last but not least, you see here we are pointing out to a relatively low scale. And so this low scale means that we should see something in PP2 tau tau, in proton-proton to tau tau. And now I will come to this later, there are interesting searches which for the moment do not exclude this effect. Actually, they are really at the border of testing this. And then, of course, if you have new physics at the TB scale involving third generation, this, of course, open up the possibility of stabilizing the Higgs sector, so something connected to the famous Higgs hierarchy problem. And as you will see now, indeed, this could fit well with the idea that the Higgs is an Ambo-Boston boson, and really there is some really new strong dynamics close by. So you see, it's a very nice, at least at the level of general EFT consideration, a very nice construction that put together a nice idea about flavor with electroweak stabilization. So it's a narrow path, because you see, we have to see things around the corner, but it's quite exciting. So let's now, this was just the FT consideration. Let's now go to model building. So if we want to describe this effect, okay, we have to address two things from a UV point of view, which is the origin of this flavor structure, and which are the mediator of this point-like interaction, which we see as point-like at low energy. So let me start with the flavor structure. And to discuss the flavor structure, let me make a step back and tell us which was the old paradigm that we used for flavor physics for a long time, especially in the context of supersymmetry. The idea was, okay, what we call minimum evaluation, that is flavor blind dynamics at the TB scale. Okay, so the idea is that, okay, there is some new physics around the TB scale, stabilizing the Higgs sector, maybe supersymmetry, but then flavor comes at a much higher scale, let's say the gut scale. So here the main idea was to concentrate on the Higgs hierarchy problem and postpone the flavor problem. So assuming that the three generations are identical copies up to high energies. This anomaly seems to say something different, something that we call the multi-scale picture. That is, really the generation are connected to different scale, and these different scale are not too far. That is, here, the scale that stabilizes the Higgs is also connected to new dynamics involving the third generation. And this is where you generate the Yukawa coupling for the third generation. And why we don't see anything, or we see small things only for the second generation, really nothing for the third generation, is because these families are connected to new physics at higher scale. Okay, so we explain at the same time why the Yukawa coupling of the light generation are small, because they are generated by high energy dynamics, and also why we don't see large deviation involving the light families, because they interact with new physics at higher scale. And this interaction with new physics is the one that also generates the Yukawa coupling. So I think this is a very nice idea, which actually was proposed a long time ago, independently of the anomalies, which fit well with these anomalies, at least qualitatively. And so what we are starting to explore now is this sector here, where we have, above the electroweak scale, we have at the few TB scale some new physics coupled mainly to third generation, with an approximate U2 symmetry acting on the first family. So the first family interact with a structure which is completely fixed by the Yukawa coupling. Okay? And so this U2 symmetry is the symmetry that protects the dynamics of the light generation. Now, coming to the mediators, I told you the second important step is which are the mediators. Well, the mediators, clearly the simplest and actually more consistent idea is to have leptoquark, because we see something big for semi-leptonic operator, while we don't see effect in 4-quark operator, we don't see effect in 4-lepton operator, and we don't see effect in semi-leptonic operator, which have a different structure, which is not the one generated by leptoquark exchange. And so this clearly tells us that a leptoquark is the best candidate, because it can generate at the 3 level what we see, while all these things are generated at 1 loop level. Now, which type of leptoquark? Again, this is something that's been discussed a lot in the literature in the last 5-6 years. And there is one candidate which is very nice, which is this U1 leptoquark that we identified back in 2015 with Riccardo Barbieri and collaborator. And it's a perfect candidate because it induced the two anomalies at the same time at the 3 level. It can really embed this U2 flavor structure. And last but not least, is the field that has a nice UV completion, because the field expected in SU4 quark-lepton unification group. As I told you, we proposed this idea of U1 as leading mediator of the anomalies back in 2015. And so it's already 7 years. And after at that time, there were many other options in place. after 7 years, basically, this is the only one that survived as a combined explanation for the two anomalies. And for anomaly is still there, still in place. And we understood much better that it's really nicely motivated. So in the last part of this talk, I want to really show you UV complete model that predict this field with the correct coupling to explain the anomalies. So let's go to UV completion. So the first important observation is that so this U1 leptoquark is the leptoquark present in the Patti-Salam group. As you know, the Patti-Salam group is a group proposed in the 70s to unify quark and lepton. So where quark and lepton sit in SU4 multiplet. So lepton is the lepton number is the 4th color. Right? This was the idea of Patti and Salam. And therefore we have the gauge group SU4 that contains QCD and B-L. So when we break SU4, we have color, the leptoquark, which is exactly this leptoquark that we need for the anomalies, and then a B-L generator. So this is perfect, but it's still not enough to describe the anomalies for a simple reason that this group is flavor blind. So this way we will have the original Patti-Salam model, the leptoquark couple universally to all the families. And so as you know very well, there are very strong bounds, for instance, from K to mu E, because we would have S going to mu and D going to E with the same strength that we would see, for instance, in B2S mu where we want to see the leptoquark. So clearly this would not work. Actually, from K mu we have a bound of 200 TeV. So clearly this is not compatible with the anomalies, but simply because in this case we have not put in the extra important information of flavor. So how to do that? The second important observation is to go beyond Patti-Salam and to have an extended gauge group where we don't have SU4, but SU4 is a subgroup, if you want, of a bigger group, which is SU4 times SU3, or better, color is a subgroup of a SU3 times SU4, where now we have a separation in flavor space. What I mean here is that this SU4 act essentially on the 3rd generation, this SU3 act only on the first 2 generations, and finally the diagonal subgroup is color. You see, this is very similar conceptually to what happens at the electroweak scale, where we have a separation in helicity. So we have SU2 left, SU2 right, or if you want hypercharge, which act differently on field with different helicity. And then finally the diagonal subgroup is the electromagnetism, which is a vector-like theory. The same would happen here, but in flavor space. So we have SU4 acting on the 3rd generation, SU3 act, this SU3, which is not color, okay, it act only on the first 2 generations, and a diagonal subgroup, which is color, which will be flavor blind. Okay? And so this breaking is the one that occurs at the electroweak scale. This breaking is the one that occurs at the diffuse TV scale. And we can go a step forward and can really, you see, this would be just is the effective theory here at the diffuse TV scale. We can go even higher and really embed this in a grand theory, a full theory of flavor, embedding this in a higher dimensional construction. So we have worked on this quite a bit in the last few years. So we can derive this 4-3-2-1 group from a model. We have an extra dimension, and we really localize the families correspond to the flavor correspond to a specific localization in this extra dimensional space. So we have the infrared brain, where we localize the 3rd generation, okay, and we localize the breaking of the electroweak symmetry. Then we have more far the 2nd generation, and finally here the 1st generation. And the breaking of the Patti-Salam occurs essentially more localized in the UV. This is why the first family doesn't feel SU4 at all, because SU4 is badly broken here in the UV. And feels and also do not feel very much the breaking of the electroweak symmetry, and therefore we have small Yukawa coupling. On the other hand, for the 3rd generation here, we have a big breaking of the electroweak symmetry, so a strong coupling to the Higgs and the large Yukawa coupling, and on the other hand, a smaller breaking of the SU4 group, and therefore some residual coupling to the leptoquark for the 3rd family. So it's a very nice construction, which also can explain the structure of neutrino masses. Now, I don't have time to enter into detail, but it's really a nice, ambitious model, where finally we can describe the Higgs as a composite state, in this case, we have to do, one step further. So we have to extend the bulk symmetry, not only SU4 times SU3, but we have to have an extended electroweak symmetry SU5, which is broken to SU4, and therefore the Higgs arise as a Goston boson. This actually is the old idea of the Higgs as a Goston boson proposed by Agassi, Contini, and Pomarol, which, however, can fit very well in this context. So this is, okay, yes, 2 minutes. Yes, let's try to converge. I think this is a very nice, ambitious model, which at the end, at the TV scale, converge just to this 4-3-2-1 model, broken to the standard model, that has to be broken to the standard model. And so the field at TV scale are the leptoquark, the Z prime, and the coloron. And it's a very predictive framework which explain all the things we have observed with a lot of prediction that can be tested in the experiment. So in the last 2 slides, or 3 slides, let me give you the prediction of this model, which can be tested in the experiment. First of all, as I said, is a general prediction. We should see some excess in PP2 tau tau, which is the T-channel exchange of the leptoquark. And here there has been an interesting search shown at Morillon by CMS, which of course I have not seen any evidence of this, but the bound that they put are weaker than expected, which means you see this is the preferred region of the anomalies, and this is the exclusion bound is the blue. So the best fit value is still perfectly compatible. So we have to follow that. Second, very natural prediction is that we should see some lepton flavor violation of the type tau to mu, both in tau decays, but also in B decays, like B to tau mu. This is a very clean general prediction. Finally, a specific prediction of this class of UV completion is that there is a heavy gluon, which is the coloron, coupled mainly to third generation. So this should see as an excess in proton-proton to top-top, which actually, with the fact that we don't see that, put the strongest bound on the scale of the model. And finally, last but not least, coming to, again, back to low energy observable, there are certain observables which are not generated at 3 level, like the leptoquark exchange, but are generated at 1 loop level. These are V2K NuNu, you see, generated by a box diagram of this type, or Bisa-based mixing. Now, in Bisa-based mixing, we don't see anything. As you know, we have a radar precision measurement, and this implies that the vector-like leptons, so these excited leptons that we see here, which come from this higher dimensional construction, have to be light because of a sort of G mechanism, and this explains why we don't see anything in Bisa-based mixing. On the other hand, here in B2K NuNu, we predict unambiguously an enhancement, okay, with respect to the standard model as a function of this mass of the vector-like leptons, which, however, you see, it's rather flat. So here there are interesting results. On B2K NuNu, okay, the present observation, it's consistent with the standard model at 2 sigma, but okay, it's if you want, it's above, which is nice. So nothing to be overexcited, but it's very nice that in the future, BEL2 really in the near future can possibly test this. And finally, here concerning the vector-like leptons, there is also again a not too significant but still interesting excess observed by CMS in final state with 2B and 2 tau, which will be the natural decay channel for these vector-like leptons. So, coming to the conclusion, sorry for the rush, I hope I give you the feeling that there is a nice picture, that emerged in 2015 of connecting the 2 sets of anomalies with the origin of the flavor structure that you see in the model is still valid. And actually has become even more appealing, if you want, because understood this also can be connected to the electroweak hierarchical problem. And it's really a motivated framework that predicts a precise pattern. Indeed, the new theoretical pattern that has emerged in the last few years that we can also connect this to the solution of the electroweak hierarchy problem. And the clear message that there must be, if all this is correct, there must be some non-trivial flavor dynamics around the TV scale involving mainly the third generation. And that really the completion of the standard model is not just a single scale model, but is a model with more scale, and these more scale are connected to the structure of flavor. So there is no contradiction with existing data, but if all this is correct, no standard effect should emerge soon, both at low energies and also at high energies. Okay, thank you. Yeah, perfect. Yeah. Yeah, thanks a lot. Very nice question. So concerning the stabilization, of course, we need to introduce some field to stabilize the construction. The scale separation is really connected to the hierarchy that you observe in the Yukawa coupling, okay? Because this profile of the field, which control the connection to the Higgs, it's in one-to-one correction to the value of the Yukawa coupling. So if you want to have Yukawa coupling of order 1 on the brain, and finally Yukawa coupling as observed experimentally, you need this scale separation. And the stabilization is very natural, so we don't have to tune parameter, but of course is an input. So we decide the scale separation according to the Yukawa coupling that we want to reproduce, okay? What is one non-trivial is actually with this scale separation, for instance, the dangerous excitation that involve the first two generation, and for instance, field that live in this bulk here that would violate flavor between the first two generation are very heavy, and therefore it's consistent that we have not seen it yet. So if you want in terms of scale, this is a TV, this is a 100 TV, and this is 10 to the 5 TV, okay, roughly scale. This is a scale separation. So the stabilization, we have seen it, it works very well, there is no tuning. There is a tuning in the Higgs mass, which is the unavoidable little hierarchy that we observe in the data. That is, the natural value of the Higgs mass would be around TV. And on the other hand, we know that this is a 100 GeV. So we have to adjust here the precise boundary condition of this field here to cancel a contribution to the Higgs mass to, say, 1% level to get the 100 GeV. This is unavoidable, and we have it. On the other hand, having this terabrennial TV scale, you see the type of warping is such that we expect Kaluza-Klein excitation, but the Kaluza-Klein excitation are at 10 TeV. So we should expect at some point to see Kaluza-Klein excitation, but this is beyond what we can do right now at the Large Hadron Collider. So the first excitation are above, a little bit above 10 TeV. So the first things you really see are the zero modes, and here the zero mode, given the gauge group, the leptoquark, if you want, is a zero mode. Okay, so this is why you should see the leptoquark, but not its first excitation, which you will see eventually if you go to higher scale.
Okay. Thank you. Thank you.
Thank you for the very nice talk. I have a question.
Sure.
Could you replace this setup, say, with intersecting the brains? Because then you solve also the problem of stabilization of the...
That's a good question, and to be honest, I don't know. Indeed, this is still a kind of effective description, okay? Indeed, we don't have really, so what happens here to higher, I mean, even if you want to go up to the Planck scale, you have to do some extra assumption. And it could be that one can stabilize this with intersecting brain, but honestly, we have not looked at that. So we just look at the simplest possible with completion, which was just, okay, a warp 5D with the scalar field stabilizing the brain. But I think it's a good point. I think, and I agree that this is still an effective description, okay? It could be that also there are more than I think one option that we strive to work is, of course, more than 5, more than simple one extra dimension, which could help, but it's more complicated. So for the moment, we have not yet come to conclusion there.
Thank you.
Hi, Gino. Thank you very much for this very nice talk. This is Sakis.
Hi, Sakis. Sorry really for not being there immediately.
Yeah, okay. Just a naive question. Can you exclude at this moment, with the current data, any loop-induced explanation for the RK?
I mean, as a general question.
As a general question, yeah.
No, I don't think you cannot exclude it at all. I mean, for sure, you can exclude it for RD star. Okay, RD star have to be 3-level. This no matter because it's too big. For RK, it's still possible to have. For instance, there are models with R parity violation where we will have RK explained one loop, so that is possible. It's completely different to what I described, but it's possible.
Yeah, and another question is at this U1 vector leptoquark model, how crucial is to have C9 equals minus C10?
Well, that's not the. You see, I think the situation is more complicated. Let me go back here. So what we see in the data is not C9 equal minus C10 only. Okay, so indeed the best fit of the data right now, there is a piece which is this C9 equal minus C10, and also universal correction to both muon and electron. So the leptoquark 3-level would induce only this piece here. But for instance, here this would be the leptoquark at one loop would induce, you see, this blob here is the leptoquark exchange. So you also have a one loop contribution, which on the other hand is universal and spoil the C9 equal minus C10 contribution. So this depends on, so some component is there, but it's not only that contribution. And this, of course, this depends a lot on the data. And indeed, as you know, now, I'm pretty sure that this central value will change. I mean, this is unavoidable also for RD star will change. And this we have to see. But some component of that, we should have it. This is also what it would be nice to have more precision information also on VS, mu, which would pin down this precisely. But this is a bit more complicated.
Okay, thank you.
Okay. The two. Okay, sorry. Okay, so, Gino, thank you. Very good talk. Now, the question is, did you check the electroweak constraints in your model?
Oh, yes, of course. Yeah, we check. Indeed, basically what defined to be, for instance, both in the EFT construction, we published already a series of papers. So one of the strongest constraints are the electroweak constraint on tau coupling, which actually are not really from high energy data, but from low energy, like tau to mu versus tau to E. These electroweak actually are still lab data. And this is one of the strongest constraints on the model, which basically set why you cannot go to very low energy. But this is basically compatible with the direct searches of the leptoquark, so it's not more stringent. Also, there are constraints from Z to tau and Z to nu, but we will look at all that, and it's okay.
Okay, thank you.
Thanks to you.
Yes, I can. All right, thanks very much. All right, so I'm going to talk about the edges anomaly and a possible solution. And I'll define what edges is, because some of you may not be familiar with it. So edges stands for experiment to detect global epoch of reionization signature. And this turns out to be actually an important experiment, as you will see. So the outline is that I'll discuss what the data is from the edges, then I'll discuss a theoretical proposal based on the Stuckelberg hidden sector model to explain the anomaly. There will be two parts to the talk. The first one would be the discussion of the evolution, thermal evolution of the universe at early times, which corresponds to high redshift. And then that would set the boundary conditions for the evolution of the universe at late times corresponding to low redshifts, which is the region where the edges experiment is. So at the end, I'll discuss some possible connection with strings and future prospects. So here is a brief history of the universe, thermal history, and the time scale that we are interested in this evolution corresponds to 10 to the minus 3 electron volt temperature and a redshift between 10 to 30. So this period, epoch, is called the reionization epoch or the cosmic dawn. Now, the 21 centimeter line turns out to be an important object for the discussion or the analysis of cosmic dawn for reasons you will see in a short time. Now, the 21 centimeter line, of course, arises from the spin transition from the triplet to this singlet state of the ground state of the hydrogen atom. And the relative population of the triplet to the neutral hydrogen defines the so-called spin temperature, which is given by Ts. And T star here is the temperature associated with the 21 centimeter line, and is 0.068 Kelvin. The 21 centimeter line in terms of frequency corresponds to 1420 megahertz, and of course it gets redshifted in the region of the cosmic dawn, and so we'll see what happens then. So here is the, I'm going to discuss now the edges data. So what edges sees is the absorption profile at a frequency of 78 megahertz, which corresponds to a redshift of about 17. And the quantity of interest is the so-called brightness temperature, T21, which is given by this expression here, which is the difference of the spin temperature minus the temperature of the CMB divided by 1 plus the redshift times the factor, which depends on the optical depth of the transition, which I will define later on. Now, on the experimental side, the analysis of Baumann et al. Found that the temperature T21 is around minus 500 plus 200 minus 500 millikelvin at 99% confidence level at Z equal to 17. And pictorially, you can see that as a big dip here at a redshift around 17. And so this is the, so what's the issue here? So that is on the next slide. Now, it turns out that Cohen et al. A year earlier had looked at this region of redshift between 6 and 40, and they found that they analyzed about 193 models within the standard cosmology. And what they found was that the maximal or the minimal value of the T21 they could get is around minus 250 millikelvin. So there is a discrepancy of a factor of 2. And the question is, why is it there? And what's the explanation? And if it is true, what does it imply for fundamental physics? And those are the issues I'm going to discuss. Now, there are several explanations which have been proposed. The three most common are the following. The first one is that maybe the CMB, background radiation temperature, is hotter than expected. The second is that maybe the baryons are cooler than what lambda CDM predicts. And the third is that maybe there is a modification of the cosmological evolution over lambda CDM. For example, inclusion of dark energy such as Chaplygin gas. Now, I'm going to focus on the possibility that the baryons are cooler, and that occurs because of the existence of a very small fraction of dark matter, around 0.3% of which is milli-charged. And it scatters from baryons, and since dark matter is cooler than baryons, the baryons are cooled. And so that is the mechanism that I'm going to discuss. However, before we go further, we can ask the question, what is the origin of the milli-charge to begin with? Now, Oldham, many years ago, in 1986, showed that with kinetic mixing, massless gauge fields of 2 U1s allow a milli-charge, which, however, is phenomenologically not viable because there are no 2 massless gauge fields. Now, later in 2004, in my work with Boris Korz, we showed that you can achieve a milli-charge with single massless gauge field by the so-called Stuckelberg mass mixing mechanism. And here is a simple example of that, this Lagrangian, which I'm going to use for the explanation of the edges anomaly. So this model consists of 3 parts, the standard model Lagrangian, plus a Lagrangian for the hidden sector, plus a Lagrangian which is mixes the hidden sector and the standard model through the Stuckelberg portal. Now, the dark sector consists of dark fermion and a dark scalar, and the gauge sector consists of a dark gauge field and a dark axion. And as I mentioned, the portal is through the Stuckelberg mass mixing, and here M1 and M2 are the Stuckelberg masses. And we'll see in a moment that this ratio of M2 over M1 is in fact the milli-charge. So in the mass diagonal basis, one finds that indeed the dark fermion, D, couples with the photon, and its charge is proportional to epsilon. And also the D quark couples with Z mu, and it has a milli-weak coupling, again proportional to epsilon. And the dark photon couples with visible quarks and leptons, and its coupling is also proportional to epsilon. And then finally, we have a coupling in the dark sector, which is the dark photon couplings with the dark fermions, and that coupling is normal size. And this coupling actually plays an important role in the dark freeze-out, which determines the relic density of the milli-charged dark matter in the early universe. Now, so as I mentioned, there will be 2 parts of the talk, evolution at early times and evolution at late times. And the evolution at early times sets the boundary conditions for evolution at late times. So let me now look at how one should do the evolution at early times. Now, here we have a model of the universe which consists of 2 sectors, the visible sector and the hidden sector. And these 2 sectors would in general belong to 2 different heat baths. The standard model would be in the temperature that we are in, but there is a hidden sector which is in general at a different temperature. So therefore, we have to evolve, obtain the thermal history of the universe by evolving with the Boltzmann equations with legs in 2 different heat baths. And this can be done only if we know the evolution of the ratio of the two temperatures, which I have defined here a function C, which you will also see later on. Now, looking into the various in the literature connected with the evolution in the thermal evolution, which involves the hidden sector, one finds that most of the works that exist in the literature evolve the hidden sector and the visible sector by assuming that the entropy, total entropy, is conserved in each of those sectors. This particular assumption is invalid, of course, if you have coupling between the two. Because there it is only the total entropy which is conserved, and that depends on the total entropy density, which is the sum of the visible and the hidden. And then you find that the density of the total density then depends on two temperatures, the visible and the hidden. And so also the Hubble parameter depends on the visible and the hidden. And the formalism to obtain the evolution in two different heat baths was obtained last year in this work in PhysRev-D, and then was extended to evolution in 3 heat baths, and this year it was extended to evolution in N heat baths with application to 4 heat baths. So in this analysis, of course, we are going to only use 2 heat baths. So I'm going to skip over all the details of this analysis, which is rather intricate, and just give you the result of what the relic density is for the millicharge. So in the evolution, thermal evolution, one finds that as a function of the hidden sector temperature, which we used in our analysis, most of the analysis as the clock, one finds that the density of dark matter is determined essentially by the interaction of the dark fermion and the dark photon. So at some time, at high temperatures, these two particles go into chemical equilibrium, and that chemical equilibrium then continues on till at lower temperatures when they depart, after which the dark photon decays and disappears from the spectrum, and then you are left with just the dark fermion, which becomes the dark matter. And then by adjustment of the parameters, we adjust this relative density to be about 0.3% of the total. And so this is the boundary condition. These are the boundary conditions that we are going to utilize in the thermal evolution at late times. So at late times, we are interested specifically in the reionization period. And there, what we need is to evolve the temperature of the dark matter and of the baryons. And here are the coupled equations for them. And they also involve the ionization rate of the hydrogen, which is Xe. So these are the 3 coupled equations. And they also involve the Hubble parameter as a function of the redshift. So there will be essentially 4 coupled equations there. Now, in these equations, you see there are QB dot and QD dot. These are the sources which depend on the Rutherford scattering, which depends on the millicharge. So the millicharge enters through these source terms. Gamma C is the Compton interaction rate, and gamma 5 is similarly defined. C is Peebles factor. Alpha B is the recombination coefficient, and beta B is the photoionization rate. Now, all of these quantities are well known in the literature, So I'm not going to dwell on them too much. And so I'm going to skip many of these slides, 3 slides here, which have to do with the Peebles factor, with the Compton interaction, and with the recombination coefficient and the photoionization rate. And so I will go straight now to the theoretical computation of the brightness temperature of the 21 centimeter line. Now, this quantity is defined by the difference between the spin temperature and the CMB temperature divided by 1 over the redshift times the factor which depends on the optical depth of transition. And here the optical depth is defined in terms of various parameters, some of which I have already defined. The new one which stands out is the Einstein coefficient for spontaneous hyperfine emission, which is A10. And NHI is the density of neutral hydrogen in the ground state. And we are going to set the spin temperature to be the temperature of the baryons. Okay. Now, here are the results. Let's focus on the middle panel. The middle panel, the dark line, the black line, is the evolution with the redshift of the CMB radiation. The evolution of cold dark matter is given by the blue line. The prediction of baryons cooling in lambda CDM model is given by the dashed orange line. And you see that the dashed orange line misses the edges point, which is given by this vertical dark red line. So in the analysis that we have done within the Stuckelberg extension of the standard model, we find that in fact there is an extra cooling from dark sector, and our prediction is this solid orange line which goes through this red line. Now this analysis is done for a dark matter mass of 5 MeV. If you choose a smaller mass, then the cooling is rapid. For example, at 1 MeV, you see it go merges with the cold dark matter line more quickly and goes through the edges line. And for heavier dark matter, the cooling is slower as one expects, but it still goes through the edges line, and this case is for 15 MeV. Now we have also analyzed the parameter space beyond just those examples I have given, where the edges effect can be explained. So here is a plot between the millicharge epsilon and the dark photon mass m gamma prime. And the regions which are not excluded by all of the constraints from experiment are the white regions and this blue region here. And the blue region corresponds to where the Rayleigh density at 0.3% is satisfied in our calculation. And this red line, the left of it, shows the region where it is possible to have a concordance with the edges result. And so in other words, there is just not 3 points there which I showed, but actually there is a significant region where one can satisfy the edges anomaly. Okay, now there is one more point which I want to mention. There was a field phi which was introduced in the beginning, which is a massless field. So therefore one has to worry what the contribution of that field is at BBN time. And we have investigated that. And now at BBN, the contribution delta N effective is given by this formula, where delta NB is the number extra degrees of freedom, bosonic degrees of freedom, which for us is 1. And then we have a factor which is the fourth power of the ratio of the hidden sector temperature and the visible sector temperature. Now, we have looked dynamically at the evolution of the hidden sector temperature as a function of the visible sector temperature. And this is this factor C, which I have introduced in the beginning. And we find that at BBN time, this factor is around 0.5. So if you put that factor 0.5 to the 4, then you find, in fact, that delta N effective is around 0.14, consistent with the experimental limit of delta N effective at around 0.2 at BBN time. Okay, so now I'm going to discuss in a little more detail the millicharge issue. So as I mentioned, millicharges do not exist in the standard model. However, they can arise in BSM, beyond the standard model physics. Now, one example of that is the Witten effect, which is the following, that in CP non-conserving theories, the electric charge of a Tuft Polyakov magnetic monopole is minus E theta over 2 pi, where theta is the magnitude of the CP non-conserving term. And this theta could be very small. And so this term could be, so this charge could be millicharge. Now, as I already discussed, the other possibility was discussed by Holdham, that you can have two U1s and they would produce a millicharge, but both gauge bosons would have to be massless. We showed that if you then produce a massive gauge boson within kinetic energy, then the millicharge disappears. And this was done in work with Feldman in 2007. So then, as I mentioned, the way to, simplest way in my mind to get a millicharge is to do the Stuckelberg mechanism proposed in 2004 with Boris Kors and myself. And what I want to discuss here is that the Stuckelberg mechanism is somehow connected in a deep way with strings. So therefore, the existence of millicharge may in fact be an indication that the embedding theory is strings. However, before I go further, I should point out there is a further constraint on millicharges, which is pointed out by Banks and Zyberg, which is that in quantum gravity, if you have a massless field, then its coupling to charge matter requires that the charge be rational. That means there is a ratio of two numbers. Of course, if that number is small, it would be very difficult to distinguish between what is a millicharge, which is a rational or not rational. Okay, so so let me now discuss the connection of Stuckelberg with strings. So it was pointed out, as is well known by Green and Schwartz, that the low energy limit of type 1 strings, the kinetic energy of the 2-tensor BMN gets modified by the Yang-Mills Chern-Simon term and also by the Lorentz group Chern-Simon term. So following this work, the Lagrangian of n equal to 1 supergravity coupled to n equal to 1 Yang-Mills in 10 dimension was then extended completely to order kappa square in this work with Chemsedin and myself, and then Berkshoff, Salam, and Susskind, and Romans and Warger. Warner. Now, here we are interested in the Yang-Mills Chern-Simon term contribution, which on expansion gives us this object here. And on compactification to 4 dimensions, reduction by dimensional reduction, one finds that this combination produces this gradient mu sigma plus m a mu, where sigma is a pseudoscalar and m is connected to the vacuum expectation value of the fluxes for the internal gauge field strengths. And now when you square it, you find that there is a off-diagonal term, which is a mu gradient mu sigma. And so this term enters into the Green-Schwarz anomaly cancellation in the following way. There is a loop contribution from ABJ, and then there is a contribution from the Stuckelberg part, which is a tree contribution, and the two cancel. And that was the famous result of Green and Schwarz. And so this mechanism is named after them for that reason. And that also corresponds to the first string revolution. Now, after this cancellation occurs, the gauge boson develops a mass. But the important point to realize is that even for non-anomalous U1s, the gauge bosons would develop a mass for the Stuckelberg, with the Stuckelberg mechanism. That is, even if C equal to 0, M is still there, and you will have a mass growth for the Stuckelberg. So, to conclude here is that the Stuckelberg is, in fact, naturally embedded in strings, and therefore string seems to be a good sort of a framework for embedding of Milli charges. Now, what are the future prospects? There are a number of experiments which are going to probe, or actually are probing in greater depth, the 21 centimeter line at cosmic dawn. These are the various radio telescopes: LOFAR, Murchison Wide Field Array, MWA, Bighorns, LEDA, Paper, Hera, and SCA, which is going to be the largest radio telescope in the world. It has 2 cores, one in southern Africa, another in Australia, with headquarters at Jodrell Bank Observatory in the UK. And it has an amazing range in frequencies from 70 megahertz to 25 megahertz, gigahertz rather. So my conclusion is that a variety of current and future telescopes will probe the cosmic dawn in greater depth and will test the edges result. If the edges result is confirmed and Milli charge turns out to be the preferred solution, it would require a paradigm shift in our view of the standard model of particle physics, as well as the standard cosmological lambda CDM model. And it seems to me that quantum gravity is in fact the right framework where to embed the Milli charge. So in a sense, Milli charge may be the signature perhaps for quantum gravity. So here is a view of the 2 SCA core centers. One is at Mir K8 in South Africa, another is at Murchison Field, Australia, here, and another is a view of LEDA at Owens Valley in California, in the range 30 to 86, which is exactly the range in which the edges effect can be tested. Okay, so that's the end of my talk.
Thank you so much for a very nice talk. Let's upload the speaker. Questions?
If not, I have some closing remarks to give. All right, so I would have to change my slides. Okay, so I'd like to now give some closing remarks to the meeting. So first of all, let me make some remarks regarding the SUSY conferences. The main motivation of this conference was to look beyond electroweak physics and ask what lies ahead. How our laws extrapolate from TeV scale to high scale, such as to the grand unification scale and beyond up to the Planck scale. Now, at the moment, it appears that SUSY is the leading candidate for such an extrapolation. And so it seems to me that it is likely that SUSY will be an element in whatever the final unified theory turns out to be. And so this is the reason for the title of the conference, Supersymmetry and the Unification of Fundamental Interactions. Now, however, I should emphasize that the final goal is the unification of fundamental interactions. And while supersymmetry appears to be a convenient vehicle to get us there, any avenue that has the potential to do that falls within the scope of this conference. So now the array of topics of the program of Ioannina SUSY reflect the spirit of the SUSY conferences. It has the topics which were discussed at this conference include supersymmetry, supergravity and grand unification, Higgs physics, quantum field theory, particle cosmology, ADS, CFT, strings, and related topics. So all these are worthy topics for discussion within the confines of our original motivation of supersymmetry and unification of fundamental interaction. And I'm glad that all those, all these topics have meet that particular motivation. Now, the Ioannina SUSY, with 200 participants in spite of the continuing pandemic and over 100 plenary and parallel talks, has been made possible by the superb organization and the hospitality extended by the University of Ioannina and by the local organizing committee. So on behalf of the participants, I take this opportunity to give our heartfelt thanks to the University of Ioannina for providing the venue for the conference and to the local organizing committee for their superb work in hosting it. And you can see here the list of the local organizing committee here who have made it possible, and we owe a debt of gratitude for them. And please join me in thanking them in a sustained applause. So now, continuing on, as you heard from Steve King in the morning, the next SUSY will be at Southampton, and it will be a milestone, as it will be the 30th SUSY conference. And the hosts are Steve King, Alexander Baliev, Stefano Moratti, and Pasquale Di Bari. And so they're all would be waiting to host you at the conference. And we are looking forward to it. So thank you all for participation, and this ends the conference. Thank you, George.
Thank you very much, Brown.
It was a pleasure to be here, and thanks for allowing me to do it remotely.
Thank you very much. Thanks everybody for being here, for the nice lectures, for the participation that made this conference possible and great. It was one of the first conferences after this pandemic, which continues, of course, but I think we were quite safe, and we hope to meet next year in Southampton. Thank you very much again.
Thank you. Bye-bye.